Hello Aries.
Hello sir, how may I help you?
Is mechanical energy conserved?
It's one of the applications of energy conservation.
Conservation of energy. No work done. So students, lecture of work, energy and power is loading. Hello बच्चों, सत श्री अकाल and namaste from my side. So as usual, okay, this was a different teaser, right, to understand the concept, to visualize the concept, right, into the very appropriate manner, and it was represented into the different way, right. As usual, physics is all about whatever it is going on into the surrounding. So that's why this time I kept something new in this teaser, right, so that it should actually correlate your what we can say, your day-to-day life. Yes, it's a part of our day-to-day life. Okay, so hope if you like this teaser, I will be waiting for all of your comments, right. As usual, all the times you are commenting beneath the video regarding all of those stuff, but this time, right, I am in search of maximum number of the comments, right, about the teaser of this specific video, right. So this champion series is for JEE and NEET aspirants, those who are preparing for the this competitive examinations. And as usual, I am Indrajeet Singh, your own physics educator, welcoming you all onto the most sensible platform, right, of an EdTech, most sensible platform of an EdTech, right. Okay, so in this champion series, we begin with units and measurement, and then we moved on to the motion in 1D followed by motion in 2D, right. Our previous lecture was based on Newton's laws of motion, and we did it very well. Now, right, we have reached to the work, energy and power, right. Lots of concepts we are going to see, lots of fundamentals we are going to discuss in this, right, and you are really going to enjoy the each and every moment of this lecture. You are going to enjoy the each and every moment of this lecture, right. So this is all about work, energy and power, right. So what we are going to discuss in this session, right, okay, everything related to the work done by all forces, right. We are going to discuss about the energy, work energy theorem, power and collisions. In my previous lecture, I already told you about, right, that spring force, right, okay, the spring force was remaining. With this, we are also going to discuss the motion in vertical circle also. But in our previous session, I already told you, right, that we are going to discuss the work done by the spring forces and all of the concepts of the spring in this specific part, right. So are you all ready? Okay, so let's begin. So as usual, as our tradition, let's move on to the first of all, right, the flow chart of this specific chapter. Obviously it is right, for sure, right, it is work, energy and power, right, it is work, energy and power, right, work, energy and power. Then obviously the bifurcation will go on into the three. Okay, the first one is work, types of work done, that is what is the classification, that is positive work done, zero work done, negative work done, right, conservative and non-conservative forces, right, conservative and non-conservative forces are also the part of this, right. We are going to discuss the graph, right, and work done by all forces, right, work done by all forces. So this is the first part, right, of the flow chart. Okay, after this, right, we are having energies, right? Most important in energy we are having, right? First, okay, kinetic energy, potential energy, right? Total energy, and most important part, that is work energy theorem. And one of the most important application of the work energy theorem, that is motion in vertical circle. Right, motion in vertical circle. Right, apart from this, right, a new thing we are going to discuss, that is about the power. Right, its relation with force, right? And lastly, we are everything regarding the collisions we are going to discuss, right? Everything regarding the collisions we are going to discuss. Okay, see, in collisions, types of collisions, right? Nature of collisions, right? Momentum conservation, it is the most important part, right? Okay, concepts related to the kinetic energy, everything, right? So this is what all about the work energy and power, right? This is all about the work energy and power, the flow chart of it. If you want to take a snap, right, I'm moving aside, right, I'm giving you all the 5 seconds. On the countdown of 5, 4, 3, 2, 1. Right, so this was a flow chart. Now let's move on to the most important part of this chapter, work. See, before moving on to this chapter, I want to remind, I want to give you like an advice. I want to create a flow of this chapter, right? So for that, I need to deliver one thing in front of you all, right? We started with units and measurement, the first chapter of the physics, right? In which the entire experimental things we did, right? All of these experimental things we did. After that, we moved on to the motion in 1D. And at that time, I already told you that we are not going to discuss with the cause. We are going to discuss, right? We are going to deal with the acceleration, but we are not completely interested, right, about the source of the acceleration. Who is providing that? The cause of the acceleration, we are not interested in that, right? After that, we moved on, right? After that, we moved on to the motion in 2D. Same, in the motion in 2D also, right? We were not interested into the cause of the motion, right? But we were brutally interested only in, yes, motion is happening and we are analyzing the activity, right? Motion is happening and yes, we are analyzing the activity. Okay? Similarly, after that, right, followed by, right, in NLM. In NLM, we discuss, yes, we discuss with the cause. Now we are going to discuss with the cause of the motion also and the energies related to it. Right, so you can understand what kind of the things are, how the syllabus is designed, what will be the flow of the syllabus, right, and how they have, right, decided that which chapter should be kept in what way, right, at what what we can say at the what part of the priority list. Okay. Motion without cause, motion in 2D without cause, motion with cause, like dealing with force. Now motion with cause, right, force and energies related to it. So now what is work? You can see the visualization in front. Okay, a student is in like you can compare it. Yet a professional or person who is working from home. Simple. This is not in work. This is an actual something you are doing, that is work. Sometimes something we are not doing, it is also a work. I'm not moving on to the technical definitions right now, just a simple definition. I am sitting idly. Am I doing the work? Yes, I'm doing the work. Lots of things, like lots of thoughts are going on into my mind, right? Okay, my mind is still active. Maybe it is not a mechanical work, I can understand, right? Okay, an abstract force is doing some work. Right, so we are not calculating it right now, right? In terms of physics, if you are sitting idly, right, there is no displacement, right? Okay, so it means work done is 0 technically, but right now I'm not discussing it that part, right? Just a simple definition of the day-to-day life. Sitting idly, am I doing some work? Yes, I am doing some work. Lots of ideas are scrolling into the mind, like this way, this way, this way, into the form of the pictures. Maybe there is a presence of an abstract force. I went to the supermarket to buy my stuff. Yes, I did the work. To do something is work in our day-to-day life. To do something is the work in our day-to-day life. Right. Now, what does a work means into the physics? Right. See, simple, if I want to define the work, energy transfer on application of a force that occurs the displacement. NCERT has relieved you all, right? They have given a simple definition of the force, work, right? The dot product of F dot D, right? And in this chapter, even sometimes the dot product is also discussed, right? But I think this is a crash course, right? So you all should be aware of what actually the dot product is, what actually the cross product is, right? How, what we can say, how to resolve those stuff. You are completely aware of it, right? So the actual technical definition of work states that whenever the energy transfer takes place on application of any force, suppose if you are applying any force, suppose you are applying a force to a specific object, now displacement occurs. It means energy transfer took place between the two parties. It means something is going on, and that is work. Now let's correlate this definition to our day-to-day life. Right. I was sitting idly into my room. Suddenly my mom called, "Beta, we need to buy this stuff because I think in the evening, right, guests are going to arrive at our house." So energy transfer took place, na? My mom commanded me. Maybe it is a kind of an abstract energy, but energy transfer took place. Suddenly I applied my internal force. I woke up and immediately went to the supermarket to buy some stuff. Yes. In the thought, the guests are going to arrive in the evening. So as because of the energy transferred by my mom, I immediately applied the force and displaced myself. Again, I am repeating this statement. As of the energy transferred, right, immediately I applied my force and moved on. And I displaced myself. It means I did something. That is work. So technically, see, lots of definitions are present in thousands of resources, right? Okay, some might be controversial, some might be not, but right now we are going to discuss, as I said, I'm going to represent that definition in physics that is really and easily understood by you all. Okay, so example. What will be the example? Technically, what will be the example of the work done? Right, let us take a very simple example, right? This is an object of mass m, here force is applied, right? Okay, so it means it is displaced by distance d. Yes, the work is done. So by reading this definition, we can say, right, if really energy transfer is taking place and somewhere the force and displacement, right, somewhere force and displacement energy, three factors are involved. It means there is the relation of work with energy also, with the force also, with the displacement also. There is a relation of a work with energy, and this is what the entire chapter is all about. This is what the entire chapter is all about. Yes, we are going to analyze the relation of the work with the energy, work with the force and displacement, because yes, definition includes all of those stuff. And what does the definition of NCERT states is just a simple thing, right? It is a dot product, right, of force and displacement. Replacing this value, we are getting it as FD cos theta, right? This is what work done is, right? It is a scalar quantity and the unit is joule. Okay, this is what the simple explanation that is given, right? And before that, into the book, right, lots of properties and commutative laws and distributive and associative laws related to the dot product are mentioned into the book. right? So this is what all about the work is. Okay, so now let's move on to the next slide. Now, as we have seen, right, we are having one formula of work done, that W is equal to F dot D cos theta. Now, see, as I said before, energy transfer on application of any force, right, that occurs the displacement. It means work is having the deep relations with energy, work is having the deep relation with the force and the displacements. So work is Fd cos of theta. Right. Now, depending on this formula, we are going to understand the classification of the work done with the three different examples, right? Suppose, let us take an example. If I am saying 0 work done, right? 0 work done. It's a very simple. See, suppose if W is Fd cos theta, then theta is angle between force and displacement. Force and displacement. Right. So in this case, in what case, right? See, depending on this formula, right? How can I say? See, there is a possibility. First, force is 0, work done is 0. Displacement is 0, work done is 0. If angle between force is also happening, like force is also there and displacement is also there, right? But angle between them is 90 degree, then also in that case also the work done is 0. So basically we are having the three criteria of the 0 work done. First, right? If the force is 0, or in another sense net force is 0, the work done is 0. Right? Second, if displacement is 0, in simple terms, right? Okay, work done is 0. Don't move on to the very controversial part right now. A very simple explanation, right? Because we are building the foundation of this chapter, we are building the base, right? So in that, right, please don't move on to any kind of the controversies right now. Just a simple explanation. If F is 0, it is a net force and blah force and phalana force and dhikana force. We are not interested in right now. We are just interested into the explanation. Yes, if net force is 0, okay. If D is 0, third. Suppose if F is perpendicular to D, how? Right? A man that is displaced into the forward, man is moving into the forward direction, right? A man who is moving into the forward direction, right? Okay, it is having a book in his hand, right? It is having a stuff in his hand, right? Force is applied right into the upward direction. Displacement, right? It is moving on into this direction. So angle between them is 90 degree. Cos 90 is 0. So in this case, if F is perpendicular to D, then also the work done is 0. Right? Then also the work done is 0. The first part. Now, second, it is a positive work done. Same concept we are going to use. It's a very simple thing, sir. If force is positive, displacement is positive, right? Or you can say they both are in the same direction. Work done is positive. Right? Okay, here there is a second possibility. If force is negative, displacement is negative, right? Even they are in the same direction. Then also, right, according to the sign conventions, I must say the work done is positive. Why? Because angle between them is completely 0. Right? Angle between them is completely 0. So yes, the work done is positive. And displacement, they are in opposite direction. Or in another sense, if you want to say the force is trying to oppose the relative motion between the two surfaces. Force is trying to oppose the motion, right? Second, theta 180 degree, right? So basically this kind of the stuff is there for work done, zero work done, positive work done, and negative work done. Okay, see, after that we are going to deal what kind of the forces. See, till now we were not aware of, right, we were not aware of the existence of the force, because till now we were only dealing with acceleration. In NLM, right, the new concept of the force was introduced. Now I am going on to move into the deeper parts of the force. How many type of forces are there? So basically we are going to deal with the two type of the forces. The one that is a conservative force, and second that is a non-conservative. Suppose this is A and this is B, right? Object is trying to move from A to B, right? How we are going to differentiate, right, the actual difference between the conservative forces and non-conservative forces? We are having the two kind of the things. We are having the theoretical explanation also. We are having the mathematical expression also. We are having the theoretical explanation also, and we are having the mathematical expression also. Theoretical explanation and mathematical expression, right? First of all, let's move on to the theoretical part first. If it is a conservative force, then I must say it is path independent forces. If it is a conservative force, then it is a path independent forces, right? Path independent forces. समझ में आ रहा है? Sorry for my word, right? It is a path independent forces. Like for example, right, the weight, it is a conservative force. The kx, the spring force, that is a conservative force. The electrostatic force, these three are the examples of the conservative forces. They are path independent forces, right? If these forces are doing the work, right, okay, then they never depends on the path. I'm going to give you all an example, right? Suppose let's take an example to understand this, right? Why they are path independent forces, right? Suppose this is point A and this is point B. Object is freely falling, right, from the height h. The first path, it's taking like this way. Second path, right, it is taking like this way. Third path, it is taking like this way. Fourth part is like this way. Four different paths the object is taking while moving on from the A to B. And here we want to prove, right, why the conservative forces are the path independent forces. Suppose here if, right, particle is moving in the first case, if particle, suppose this is first, this is second, this is third, and this is fourth. In the first case, suppose if particle is moving, right, so can I say work done, that is equal to force into the displacement. Force is acting into the downward direction, displacement also in downward direction, right? So it's Fd cos theta. So here work done, that is equal to mgh. First case, right? Second, again I'm going to use the same formula, F dot d cos of theta, right? Okay, now see, displacement is like this direction, right? Force is acting in this direction, right? Force is acting in this direction, but displacement is moving on in this direction, right? So can I say, right, here the work done, force is mg, displacement is, suppose if I'm using the triangle, this is 90 degree. Suppose if I am using the triangle, suppose if this h is, can I say this is h by cos theta? So displacement h by cos theta dot cos of theta. Again work done is mgh. I'm sorry. I'm applying the simple triangle part. Suppose if this is a theta, chalo, let's take an example. We are not taking that part as a theta, right? We are not taking that part as a theta. Okay, suppose this is an h, right? Suppose this is an h, right? So can I say cos theta that is equal to h by hypo, right? This is a displacement that is an hypotenuse. We are taking this as theta, right? I'm sorry, we are taking this as theta, right? I'm sorry, right? So what will be the hypotenuse, the displacement, that is h by cos of theta, right? The same thing we are replacing here, displacement h by cos theta, right? And this is work done. The third case, suppose the height is h1, h2, h3, h4, h5. So can I say work done that is equal to mg h1 h2 dot 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 h5. So here again the work done will be mgh. The fourth case, dw is equal to f dot dx. Replacing this value here also we are getting it as an mgh. So in all of the cases we have taken the different paths, right? Right, we have taken all of those paths, right? Okay, but still, right? That this thing is happening, right? It is not depending on path. Whatever the work done is there, it is not depending on the path. So that's why this mg is told as it is a conservative force, because it is a path independent force. It is the path independent force. So this is what we proved. Okay, now see, conservative forces, they are path independent forces. Second, if I'm talking about if it is a non-conservative force, right, then it is path dependent force. The best example of the path dependent force that we are going to use in this chapter is friction, right? Friction. So suppose, let us take an example. If a non-conservative force is doing the work, right, W3, W4, W5, like that. If non-conservative forces, like if non-conservative forces is doing work from multiple paths, right? If for a non-conservative force, W1 is not equivalent to W2, is not equivalent to W3, is not equivalent to W4. Because non-conservative forces are path dependent forces. And if for a conservative force, right, W1 that will be equivalent to W2, that will be equivalent to W3, and so on, because they are the path dependent forces. And whatever path you are taking, at last it only depends on initial and final point of the motion. Yes, the most important part I'm writing, they depends on initial and final point of the motion. Initial and final points of the motion, right? Mg is a work done, right? Mg is a force that is a conservative force. Kx is a force that is a conservative force, right? All of this stuff, they are the conservative forces. Okay, so now this thing was remaining into the previous session, and we told you all, right? And before moving on to that, I want to discuss, right? Okay, before moving on to that, I want to discuss, right, what kind of the forces, what will be the, as we all saw about the nature of the forces, right? But there is one more classification, that work is done by constant force or work is done by the variable force. So here, work done by if work is done by constant force, then we are not having, right, we are not in worry of, right? So work done that is equal to F dot D cos of theta. Here F is constant, right? F, we can say net force, right? F is constant, F is constant, F is net force, right? Okay, and there is a possibility, right? There is a possibility in systems more than one force X. So for that reason, in the previous part of this session, in the beginning of the session, we didn't move on to that much technical definition, right? I just explained that F dot T cos theta. But here, the actually it state that suppose it is a constant force, right? Then F is always a net. Because we want to generalize those things, right? We want to make physics unbounded, right? So for that reason, there is a possibility, right? There is a possibility that more than one forces may act on a system. So in that case, which force is going to do the work? Yes, the net force is going to do the work, right? Suppose if work is done by the variable force. Let's have an example of it. Suppose this is a path A and B. Particle is at this position right now. Okay. Suppose if, right, particle is moving onto the path A and B. Right. So here, okay, suppose if this variable force is doing the work. So it is defined as dW is equal to the small displacement of the particle dr is measured, right? So here the force is acting F dot dr, where dr it can be dx of I, dy of j plus dz of k. All of this thing, right, we are going to discuss into the sums, right? So this is what happens. This is the formula that we are going to use, right? Variable force, it means that force that depends on other motion parameters. Force that depends on other motion parameters. Right? Like forces depending on time, forces depending on velocity, some X relation is given, right? The best example for the work done by the variable force. Force is, let us take an example, 10 plus 2y, right? Suppose F is determined as 10x of I plus 10y of j plus z of k, like this way. This all are the examples. Either they are depending on the displacement or a respective motion parameters, right? Then those kind of the forces are completely variable forces, right? And in the cases of the work done by variable forces, this is the phenomena we need to follow, right? This is the phenomena we needed to follow. Now, why I wrote that part? Spring. We need to calculate the work done by the spring force. See, first of all, if you want to tell about the nature of the spring, right, then it is a kind of a helical structure. As you can see, we are having whirls, right? So this is the kind of the helical structure, right? We are having the winding kind of things, wind, whirls, right? We are having this kind of thing, right? So it is a kind of a helical structure. Suppose, let us take an example. If a force is applied at the one end of the spring, right, and it is getting elongate, or you can say we are facing an elongation into the spring on application of any force, right? So in this case, what will happen? Suppose if you are trying to elongate a spring, right? Okay, so in that case, first of all, this much part of a spring, right, either you are trying to elongate it, right, or either you are going to compress it. First of all, this small part, the dx part of the spring, right, okay, it will try to elongate. After that, slowly, right, okay, slowly, this dx is increasing to some specific value. Suppose at t is equal to 0, force is applied. At t is equal to t1, we are facing the displacement of dx1. at t is equal to t2, we are facing the displacement of dx1 plus dx2, right? Similarly, at t is equal to t3, we are facing the dx1 plus dx2 plus dx3. At an end, we are facing, right, okay, the displacement of x. That is a maximum elongation into the spring or maximum compression into the spring. So slowly that displacement occurs and value is going to increase. Right. So now, as because of this, suppose if spring is getting elongated or getting compressed, as it is an elastic object. So in elastic, the elastic objects are having a one kind of a property of restoring themselves, right, on its original position. Right. Whenever the external force is applied to the elastic objects, obviously we can feel the change in configuration in them. But whenever that force is removed, right, obviously that is for sure there is a presence of a restoring force that always bring that system in its original configuration, bring back to the system in its original configuration. And that force is restoring force that always tries to restores the spring or any elastic object into the original position. So suppose if F, can I say, is directly proportional to delta x. Now this kx is always opposing the elongation or the compression of the spring, right? So here it means that if value of the x is increasing or decreasing, it means that kx is not a constant force, it is a variable force, right? So here the spring force is defined as minus kx. The negative sign appears because it always opposes the compression or the elongation of the spring. Because that this kx is a kind of the restoring force, right, that always helps springs to restore its original position on removal of an external forces. So this is the variable force, and how we are going to calculate the work done for the variable force, that is F dot dx. Similarly, dw, that is equal to negative of kx of dx, right? So here on integrating, we are getting it as negative of the change in potential energy, where u is equal to half kx square. Or in another sense, if you want to define work, right, we can say work done by the spring is negative of half, right? Or general definition, if you want to write down, right, a general definition of the force, this is what the this is, just hold on, I'm writing down the general definition of the force, right? What happened, bro? I think as because of this visualization this happening, right? Just hold on, guys. I'm sorry. Okay, just hold on. Okay, if I want to generally write the definition, right, I must write it as, come on man, shit, just hold on here. Work done, that is equal to negative of half k, right, x final square minus x of initial square, right? So this is negative of half, right, x final square minus, this is what the general definition of work done by the spring forces is, right? Okay, now let's move on, right? Okay, see, first of all, let's revise some of the fundamentals related to the work done. We started work with the simple definition and we saw, right, its dependencies, right, its relation with the energies, forces and displacement. First of all, we moved on to the different types of the work done, whether the work done is positive, work done is negative, right, and all of this stuff, right? Work done is positive, work done is negative, and all of those things, right? Okay, work done is positive, work done is negative, right, and the respective classification. And after that we moved on with the conservative and non-conservative forces, right, and after that we moved on with the work done by the spring forces, right, and we saw work done by the constant forces and work done by the variable forces. Now we are going to see the sums related to it. A force F is equal to 20 plus 10yx on a particle. There is another way also, right? There is another way also, right? To actually define that which force is conservative, which force is non-conservative. As I told you before that there are two explanations, right? Whether how you are going to classify in between the conservative and non-conservative forces. So one that is a theoretical explanation, the second one that is a mathematical expression. So after this sum, we are going to see the mathematical expression, and NEET 2019, right? One sum related to the work done has been asked, right? The work done, the energy conservation are the most important aspects and most important concepts of the physics. In this chapter, you are going to deal with the work energy theorem and energy conservation, right? In rotation, you are going to deal with the energy conservation, right? In gravitation, you are going to deal with the energy conservation. In solids, you are going to deal with the work done, right? In this one, fluids, you are going to deal with the work done. In SHM and waves, right, you are going to deal in waves. There is a less part, but in SHM, you are going to deal with this kind of things and energy conservations, right? In 12th electrostatics, you are going to deal with the energy conservation. Capacitors, you are going to deal with the energy conservation. There is a difference of force. Right, in magnetism, you are going to discuss with the work and torque and potential energy, everything, right? Okay, so lots of things are there. So this plays the most important role, right, into the entire physics, the energy conservation. Now see, force is acting like 20 plus 10 by. How you are going to classify the difference between the constant and variable force? See, here the force is indirectly depending on the y part. And here y is changing from 0 to 1. So immediately by seeing this equation, right, we got into the mind, yes, this is a case of the work done by variable force. And for work done by the variable force, we are going to use this equation dW, that is equal to F dot dr. Right. So here W, can I say, let's integrate it from initial position, right, to final position, F dot dr. Initial position to final position, that is F dot dr. So can I write it as work done? Now here displacement is going on only in the y direction. So here x coordinate is 0, y coordinate is 0. X coordinate of initial is 0, x coordinate of final is 0. Y coordinate of initial is 0, y coordinate of final is 1. Z coordinate is 0. This kind of the displacement it is going on. What is the formula of force? That is 20 plus y. Now how we are going to replace the dr, that is dx of I, dy of j plus dz of k. Now as according to the dot product, you all are aware of, I dot I is 1, I dot j is 0, I dot k is 0, j dot j is 1, k dot k is 1, irrespective of all of those things, right? So now how we are going to resolve this? Again, right, work done, that will be, right, 0, 0, 0 to 0, 1, 0, right? Okay, now in this thing, right, you can see this equation, all of those things are getting 0, only one thing is going to remove, that is 20 plus, right, 10y into d of y. The product of these two factors are only going to be 1, else the term will be completely 0. So here if only y term is present, so can I replace this limit, right? Can I replace this limit from 0 to 1? Obvious thing it is, right? Can I replace the limit from 0 to 1? So the limits are replaced from 0 to 1. So your work done, that is equal to 20 of y plus 10 of y square by 2, limiting from 0 to 1. So here work done, that is equal to 20 of y plus 5y square, limiting from 0 to 1. Right. So can I say work done, that is equal to 20, right, plus 5 minus 0, right? So this work done, that is equal to, right, 25 joule. The actual work done, that is equivalent to what? 25 joule. And that is a perfect answer for this specific question, right? This is how, right? Apart from this, we are having the new different another calculation of the graph also. But moving on to the most important part, that is how you are going to identify whether one force, right? Suppose, let us take an example. If I am giving the forces F, that is equal to x of I plus y of j plus z of k. Suppose in question this equation is given and they have told us, right, identify whether this force is conservative or not. So what is an actual condition? Condition to check whether the force is conservative or not. Conditions to check whether the force is conservative or not. For that, we have to move on to the concepts of the partial differentiation, right? Partial differentiation states that there is a small difference, right, into the differentiation and partial differentiation. In partial differentiation, see, suppose differentiation, it is d by dx. Partial differentiation is del by del x. For conservative forces, we are always having this partial differentiation. Why? Because they are path independent forces and partial. See, in this there is only one, in physics point of view, right, we are having only one difference, right? In the differentiation we are having the chain rule, but in the partial differentiation, right, we are not having the chain rule. Let us take an example, right? Suppose if it is given d by dx of x square plus y, what will be the answer? 2x plus dy by dx. This is an actual concept of in differentiation, right? But if we are same, right, partially differentiating this with respect to x, our answer will be 2x plus 0, 2x. We are not having any kind of the chain rule, right? We are not having the chain rule, right? So this is a concept of partial differentiation. One, it is a concept of partial differentiation. Second, differentiation. For conservative forces, we are always having the partial differentiation. Why? Because they are path independent forces, right? They are not path dependent forces. So what is a condition? Del f of x with respect to del y. Del f of y with respect to del x. Del f of z with respect to del y, right? Del f of x with respect to del z, del f of z with respect to del. These three conditions should satisfy for a force, for a three-dimensional force, that is fx of I, fy of j plus fz of k, right? For this force, suppose if you want to identify this force is conservative or not, these three conditions should get satisfied. Then and then we can say, right, that this kind of the forces are conservative or not, right? This condition should satisfy. The x component of the f, right, should be partially differentiated with respect to y. The y component of the f should be partially differentiated with respect to x. If this both are getting equal, first condition is satisfied. Second, x is y is differentiated, partially differentiated with respect to z. Z component of the force is partially differentiated with respect to y. If this is equal, these two values are equal, then second condition is also satisfied. If x is partially differentiated with respect to z, x means the x component of the force. The z component of the force is partially differentiated with respect to f. If again these two values are getting equal, right, the third condition is satisfied. If the three of the conditions are getting satisfied, yes, we can say this force is a conservative force. You can see x with respect to z, 0. Z with respect to x, 0. Y Y component is differentiating with respect to Z, 0. Z component is differentiating with respect to Y, 0. X with respect to Z, 0. Z with respect to all, or getting all of these three conditions are satisfied. So it means yes, this force is the conservative force. Right, it is a kind of the path dependent force. Apart from mgkx, right, this kind of the questions are also there into the examination, and this is a black screen, right? Okay guys, so if you want to have a snap of it, I'm giving you, right, 5 seconds on the countdown, right? 5, 4, 3, 2, 1, that's it. Now let's move on to the second sum. Graph. What do you actually want to tell about the graph? Let's move on to it. Suppose it is a force versus displacement graph, right? Force versus displacement graph. Two conditions may arise. We have seen two kind of the force. First one, that is a constant force, right? Or second one, that is a variable force. So suppose if we are having force as this, like this way, we are having the case of the uniform graph. The force value is changing, right, but it is changing uniformly. If it is not changing, it is constant, and if it is changing, it is a uniform change, right? Okay, then we must say work done that is equivalent to area under the graph, area under the fx graph. It means simple, this is right, differentiated, like this is A1, this is A2. So here work done that will be equivalent to area under the curve A1 and A2. The x that is positive, it is positive, right? Two cases. First, f is constant. Change of f is uniform. F is constant, the change of f is uniform. If it is a case of the variable force, how? Suppose this is f versus x graph, right? And it is moving like this way, right? This is what a variable force is, na? This is what a variable force is all about. So for that reason, a small infinite strip is plot, as this reminds us about the concept of area under the curve that you have seen into the mathematics also, into the basic mathematics also, right? And even you have seen into the physics also. The small dx is plot, and for that the work done is f dot dx. In another sense, it is integration of f dot dx. If the force is only acting into the x direction. Now if force is acting into the right, then it is f dot dr, right? This thing we have already seen. This is respective forces acting into the x direction, we are having dx. If force is acting only in y direction, we are having dy. So in that case also force will depend in x also only, right? If force is having three components, then we are having the general term. If force is having either x, either y, it is depending either on x part or either y or z, then we can use this individual term also, right, to ease our calculations. So in this case, x initial to x final, right? Suppose this is a x initial, this is an x final. This is how area is calculated, right, by using an integration. Area is calculated by using an integration. So this is how the graph based sums are solved. F is a force moving in the straight line, varies with the distance as shown into the figure. You can see. While displacing from 3 to 7, force is constant. From 7 to 12, force is changing, but the change is uniform. That's why we are having the straight line graph. So in this case, and obviously, right, we are going to calculate this is A1 and A2. So for this, work done, that is equal to area under the force versus displacement graph, right? So in this case, work done, we are having area A1 plus A2. So here work done, that is actually equivalent to what? A1. A1 is 4 into 2, right? The area of this rectangle and plus area of the triangle half base into altitude. Altitude is of 2, right? So here work done by the force, right, is equivalent to 13 joule in between this two till 12 meter of the displacement. How much amount of the work is done? 13 joule. That D is the perfect answer for this specific question. D is the perfect answer for this specific question. A very simple thing. This is the case of the constant or the forces getting uniformly changed. Now see, we are having the case of the variable force, and a new thing we are going to learn from this concept, from this sum, a new thing. Okay, students are always in a confusion, right? Students are always in a confusion. Who is doing the work, right? That thing, right? Okay, one new, in summarized form, one new thing we are going to see in this sum. Let's see this. It has been asked in 2006. A body of mass 3 kg is under the constant force which causes the displacement. You can see this word here. This is a mind blasting word. A constant force that is changing the, that causes the displacement. I'm having one question in your mind, right? One question. Work is done by only one force or work is done by more than one. Causes a displacement. The force that is causing the displacement is only one, or it is the net force that is causing a displacement. We are having the two possibilities in front. In question, it is not mentioned whether the displacement that is happening only is because of one force. There is a possibility 1000 forces are acting on that object, and after doing the resultant of all of those 1000 forces, we are having one value, that is net force, and that is the responsible for the displacement. Mark these words: causes a displacement. Causes a displacement. You can mark those words, please. In none of the question describes in the statements whether the single force is involved, right, or whether the multiple forces are involved. So in that case, generally whenever, see, the displacement is depending on time, 1 by 3 t square, right? We are aware of the simple definition of the force. So generally what students do, right, this let's differentiate this equation with respect to time. We are getting velocity as 2 by 3t. Again differentiating this stuff, we are having acceleration as 2 by 3 meter per second square, right? We got our acceleration, we are going to multiply with mass, right? And for a time, right, in 2 seconds, we are going to calculate the displacement. Yes, we got work done is equal to MAD. Wrong. You all are doing this mistakes. W is equal to MAD, right? Mass is 3, acceleration is 2 by 3, displacement at the 2 second is 1 by 3 into 2 ka square of 2. This is wrong, wrong, wrong. We can follow this procedure when it is clearly mentioned that only one force is acting. In that case only we can follow this procedure. But here, right, under a constant force, there may arise a possibility. Here it is mentioned it is under the constant force, it's not a big deal. But the difference I want to tell you, this is what the general, suppose if I am reframing the statement, okay, listen it carefully. A body of mass 3 kg is under, right, an application of a force, right, okay, and its displacement is changing. Here it is mentioned that it is under the constant force, right, which causes the displacement. I'm just reframing. The displacement depends on time, like this way. Things will get changed. So what is the solution of this? So guys, please read this kind of questions carefully. These questions are very easy, right? This kind of the questions are very easy, but we need to just have a click of it. How we are going to solve this? See, we are not aware of whether one force is involved or whether the multiple forces are involved and they are giving the resultant as the net. So for that, we are not depending on the force, but we can depend on energy. Work done, that will be equivalent to change in kinetic energy. Yes. We can't depend on acceleration because we are not aware whether this, we are not aware whether this acceleration we are getting, it is a net acceleration or not. Right. So for that reason, what we used to do, we can depend on velocity. We are not relying on acceleration, but if we rely on change in velocity, right, then who is changing the velocity? Net force. Right. Okay, we have to grab like this way. We have to move, don't move like this way, you have to like this way. So in this case, suppose if the displacement is giving like s is equal to 1 by 3 t square, the velocity we are getting it as 2 by 3 of t by differentiating this term. Now in between t is equal to 0 to t is equal to 2 seconds, how velocity is changing? At t is equal to 0, v1 is 0, at t is equal to 2, right, velocity is 4 by 3. Now work done, that is equal to change in kinetic energy. So that is half m, right, v final square minus v initial square. Initial is 0, right, mass is 3, final that is equal to 16 by 9. This 3 is gonna cancel. We are having work done as 8 by 3 joule. Right, we are having work done as 8 by 3 joule. Right, 8 by 3 joule. Suppose if we are following this procedure, so we are having MAD, right, mass, this 3 is gonna cancel. Again in this case also we are getting 8 by 3 joule. But this is not an approach. See, why we are getting the same answer in both of the procedure? Because it is given, it is only under one constant force that causes the displacement. That's why in this procedure also we are getting the 8 by 3 and the actual procedure also we are getting the 8 by 3. Suppose if I am reframing the terms now, right, the answer will be different. Okay. In this case I can understand in both of the, but this is not an actual procedure. This procedure we need to follow when we are aware of how many types of forces, how many number of forces they are acting on the system. But this is a regular procedure for all kind of the questions, right? Again we got the new question, a force F is acting, again say this is F versus X graph, right? Okay, the force, okay, the work done by the force in moving from X is equal to 0. See, work done, that is equal to area under the Fx graph. Area under the Fx graph. Right? Area under the Fx graph. Right? So can I say this is area is A1 and this is A2? Right? So can I replace this value as work done, that is equal to A1 plus A2. A1 is the area of the rectangle, that will be 3 into 3. Right, this is a 3 now, and this height is also 3. And this is half base into altitude. Base is from 3 to 6. Right, again this is from 3 into 3. Right, so this is 9 into 3 by 2. Ouch, man. Right, so this is approximately 13.5 joule. Okay, so 9 3s are 27 by 2 na. It's 13.5 joule. This is the work done. The B is the perfect answer for this specific question. B is the perfect answer for this specific question. Right, so this is what work done, the area under the fx graph. Okay, okay. A position depends on force like this way. Sorry, force is depending on the position. The work done is, see again you can see what is the value of the force F, that is equal to 7 minus 2x, right, plus 3x square. This is a question of the variable force. So for a variable force we are having the formula of work done as this way. Now here we are aware of forces depending only on x. So we can directly use this formula. This is a work done F dot dx, right? And similarly, right, this work done, right, can be defined as, right, like this way, from 7 minus 2x plus 3x square, right, dx. What is the limit given? Given from 0 to 5. Right, you can solve this and get the answer. It's not a big deal. It's a very simple question. Right, it's a very simple question. You can see in competitive examinations, especially from the work done, this kind of the graph based question, right, and this kind of the the use, what you can say, the questions based on the calculus methods are also there, right? Okay, the actual difference I already showed you all, right? So this was the first part. Now in the previous chapter we have dealt 6 type of forces, right? In the previous chapter, we have dealt with the 6 type of forces. First one, it was mg. Second one, it was friction. Third one, it was pseudo force. Fourth one, it is normal reaction. Tension. Right, mg, friction, okay, spring force. These 2 are the conservative forces. Rest of them, right, are having their different natures, right? So if this type of the forces we have dealt with, right, so I want to ask you all the question whether these forces are doing work or not. Whether these forces are doing work or not, because for a work we are having the very simple formula F dot D of cos of theta, right? So I want to ask you all whether this kind of the forces are doing or work or not. Is it good to move to the explanation of the individual part, or else we can directly move on, right, to the work energy theorem? We can directly move on to the work energy theorem. What it states, what actually the work energy theorem is, what actually it states, right? Let's see this stuff. So we had moved on to all of the concepts related to the work done, the respective classification. And it's time to move on for the work energy and theorem, right? What it states, what is an actual definition of the work energy theorem, right? What its actual expression is, which expressions, right, we are going to use in solving all of those questions, right, that has been already asked into the competitive examination, right? So there is only the one single approach for work energy theorem. First of all, right, what it states, work done by all forces will change the kinetic energy of the particle. The resultant of all. Right? A very simple explanation I'm going to give in front of all. Let us take an example. This is an object of mass m. One force that is acting in this direction, right? One force that is acting in this direction, right? The third one that is in this direction. Three forces are acting. A very simple explanation of the work energy theorem. Or in another sense, let us take an example. Let's take the known forces, right? Let's take the known forces, right? Let's take the known forces. Okay, see, suppose here there is a presence of external force. Suppose if the surface is rough, so friction is acting into the backward direction. Here we are having normal, this side we are having mg. So I want to ask you all whether this particle is getting displaced or not. Yes, it is getting displaced. It is mentioned into the question. If the particle is getting displaced from one position to another position, transfer of energy is getting, right, takes place, right? So it means something is happening, right? Here getting the output, right, as a work. So if the particle is getting displaced from one point to another point, if particle is getting displaced from one point to another point, it means it is a very, very, very simple thing, right? Okay, work is, look, we are getting the output as a work done. But as you can see, we are having four forces here. First, normal. Second, friction. Third one, mg, and external. Who is involved in getting an output? Who is involved in the summarized form, if I can say, who is involved into the resultant work done? I must say all of those are involved. That's why I have written. Somewhere it is written as work done by the net force that is equal to change in kinetic energy. No. It is, right? We can't avoid it, but actually that makes sense. Right, this is a generalized thing what we are discussing. In some of the books, right, in some of the resources it is written net, the word that is used, net, right? But here work done by all that will, right, change in kinetic energy of the particle, right? Work done by all that will change in kinetic energy of the particle, right? Work done by all. Now work done by all, it means here friction is doing something, normal is doing something, mg is doing something, right? External force is, all of these are doing the work and they are changing the kinetic energy of the particle, right? This is a case to case based explanation, right? This is what an example I am giving. Why I have written, see, for a work energy theorem there is only one statement, right? This one. Why I have written this? I'm explaining this statement. After that, we will have a generalized explanation or a generalized expression. After that, I will show you there are some basic steps to apply the work energy theorem for all kind of the questions. There are some basic steps, right? So here, normal is perpendicular to the displacement, mg is perpendicular to the displacement. So work done by normal and mg will be 0. So here work done by external, that is delta k, and work done by friction. So here we are having friction is doing something work, some external force is doing something, and that is resultant of both of the work done, that is changing the kinetic energy of the particle. That is changing the kinetic energy of the particle. So this was the explanation of the statement. If one activity is going on, we are analyzing in that activity. So in that single activity, we are not having only one force, right? We are having the n number of forces. All of are contributing in work done. Maybe someone is having the 0 contribution. Maybe someone are having the, what we can say, less amount of a contribution into the work done, but contribution is always there, right? Okay, so now what are the steps? What is an actual expression for the work energy theorem? right? What are the steps and what is an actual explanation of the work energy theorem? So first of all, see, before moving on to the work energy theorem, you all are completely aware of what is the potential energy, what is the kinetic energy, right? Okay, how potential energy is defined with respect to the reference point, what is the change in potential energy, how we can correlate the potential energy with respect to the conservative forces, right? If you are not aware of, then don't get worried. After this explanation, I'm going to explain that part in short. As I said, work done by all forces will change into the kinetic energy of the particle. All forces means what? Somewhere conservative forces there, somewhere non-conservative forces there, somewhere external forces there. All will make a resultant, right, change, right? And that resultant change will change into the kinetic energy of a particle. Whenever we are having the conservative force, it means that mg, kx, electrostatic forces are one of the examples, some of the examples, right? So in that case, if I want to tell you about that, whenever the conservative force is doing the work, it is always stored into the negative of the change in potential energy. One of the examples I gave you just a minute before, while we were deriving the equation of work done by a spring. Right? We get it as a negative of change in the potential energy, right? So can I rewrite this term as negative of change in potential energy plus work done by non-conservative, that is equal to external, and that is change in kinetic energy of the object. So in another sense, work done by non-conservative force plus work done by external force, that is equal to change in kinetic energy plus change in potential energy of the particle. This is what the actual statement is. In all of those questions related to work, energy and theorem, we are going to use this stuff only. In all of those questions, right, related to work, energy, theorem, right, we are going to use this equation only, but into the different formats, right? Now, what is an example of the non-conservative force? Can I say friction? Work done by friction, work done by external force, that will results as change in kinetic energy and the change in potential energy of the particle. What are the steps to solve this kind of the sums? Right? I'm going to show you all some steps, and the same steps, using all of those same steps, we are going to solve more than 10 sums related to the work energy theorem. More than. Right? More than. Okay. Now, what are the steps? The same work energy theorem we are going to use for the chain problems, because we are having the two kind of the bodies now. One, we are having the rigid bodies, and second, we are having the particles, right? So here, step one, steps to solve this kind of the questions related to the work energy theorem into the very convenient manner. First of all, follow the general expression, right, of the work energy theorem, right? What does the general expression states? That is work done by friction plus work done by external, that will result in change in kinetic plus change in potential energy of the particle, right? The resultant will, right, change in kinetic and change in potential energy of the particle. Step 2, check the presence of external and non-conservative forces. Second step, right, you have to check the presence of the external and non-conservative forces. Check whether the friction is present or not. Check whether we are having any kind of the non-conservative forces or not. Suppose if work done by the friction, it is 0, and work done by external force is 0, it means that delta K plus delta U, it is 0. Third step, if these two are absent, then we are having the mechanical energy as conserved. Step 3, Now in the case of the conservation of mechanical energy, can I write this equation? K initial, U initial, K final, U final, right? This is it means total energy is constant. This is the total energy at the initial position, right? And this is the total energy at the final position. The total energy at the initial position and total energy at the final position, right? Step 4, evaluate it. This is the best way, right? Okay, to solve all of those sums related to the work energy theorem. All of those sums. Simple explanation we need to give, a simple explanation, right? Just check it on. See, if there is a presence of the friction or the external forces, we are having no option, right? Okay, we have to use this equation only. That is a generalized explanation of the work, generalized expression of the work energy. Now, suppose if friction is absent and external force is not present, whatever the energy, see, as I said, work done, it means energy transfer is going on. So whatever the energy transfer that is going on in between, right? If this friction, the non-conservative forces and external forces are absent, right? Then whatever the energy transfer it is going on between kinetic and potential only. Somewhere kinetic is going to be minimum, somewhere potential is going to be minimum, somewhere kinetic is going to maximum, vice versa. So in that case, we have to directly use this expression, right, of a conservation of mechanical energy, in which at the initial point and the final points. How to apply this expression, we are going to say in this sums. How to apply this expressions, we are going to use this in the sum. But using all of those two, we are going to solve more than 10 sums in this session. So those who are having the great confusion while solving the sums of the work energy, right, the energy conservation, right, kindly stay till end. You are really going to learn a lot from this, right? Because this is only the important part, right? First, right, 3 to 4 PYQs we are going to see, and after that I'm going to show you all, right, all of the great and awesome concepts. Particle of mass 10 gram, it is moving along the circle of radius. See, mass of the particle, that is 10 gram. Can I say it is 10 to the power minus 2 kg? Yes. Radius of the particle, radius of the circular path, that is 6.4 centimeter. That is 6.4 into 10 to the power minus 2 meter. With a constant tangential acceleration. With the constant tangential acceleration, it is moving onto the circular path. With this sum has been asked in NEET first in 2016. Even this kind of the sum has already, right, been asked in AIMS examination. Right, I think in 2015 or 16, this kind of sum was also there, in which into the concepts of the circular motion. If you all have seen my previous session of motion in 2D, then I've already mentioned, right, while solving the case of the circular motion, right, that this kind of the sum has already been asked in AIMS also, and see in this NEET also, right? How work energy theorem is we are going to use for the non-uniform circular motion, see. Right. What is the magnitude of the acceleration? See, initial kinetic energy is 0, right? Okay, at the end of the second revolution, after completing 2 revolutions, right, the final kinetic energy we are having 8 into 10 to the power minus 4 joule. So what is the tangential acceleration of the particle? Simple. This is the case of the work energy theorem. See, work energy theorem states work done that will change into the kinetic energy of the particle. The same, see, in all of the question, as I said before, only this explanation, this expressions we are going to use, right? Either this or this, either this or this, and we are going to solve all of those sums, right? Work done that will change in kinetic energy of the particle, right? Okay, see. Work done. Okay, the particle of mass 10 gram moves with the radius 6.4 centimeter with a constant acceleration. Now what is the magnitude of the acceleration? Okay, now what is the change in kinetic energy of the particle? Right? Okay. In another sense, we can say, can I consider this as equation number 1? Yes. Now, change in kinetic energy, that is equal to K final minus K initial, that we are having 8 into 10 to the power minus 4 joule. Right? Now this, can I write it as half m V final square minus V initial square, that is equivalent to 8 into 10 to the power minus 4. Right? So V initial is 0. So V final square, that is equal to 16 into 10 to the power minus 4 whole divided by m. Right? Can I consider this is equation number 2? In question it is mentioned the particle is moving on the circle of this radius with the constant tangential acceleration. It means whatever the work is going on, it is as because of that tangential acceleration. So can I say work done, that is change in kinetic energy, right? This is force into displacement, that is equal to change in kinetic energy. Now this is happening at the end of the, right, this is happening at the end of the 2 revolutions, right? So force, that is mass into the tangential acceleration, right, because this force is only responsible for the work done. After 2 revolutions the kinetic energy is getting changed. It means it is twice into 2 pi r. The total distance in 1 revolution is 2 pi r. For the 2 revolutions it is 2 into 2 pi r, and that is 8 into 10 to the power minus 4. Right? So here tangential acceleration we are having, right, 8 into 10 to the power minus 4 whole, right, okay, divided by mass into 4 into pi of r. Right? So it is 8 into 10 to the power minus 4. What is the mass of the particle? Right, it is 10 gram. In another sense 10 to the power minus 2 kg. 4 into pi, right, into r, 6.4 into 10 to the power minus 2. Right? So either you can directly apply this formula, right, or here you can use the third equation of motion to calculate the tangential acceleration. This is the first procedure and this is the second one. Directly you can use the conservation, right, this direct the expression of, right, W is equal to delta K, or you can use, you can just evaluate this, right, and you can use this the third equation of motion, because it is given acceleration is constant tangential acceleration, right? So we can use this equation also. From here also we are going to get acceleration as 0.1 meter per second square, right? And from here also we are going to get the tangential acceleration as approximately equivalent to 0.1 meter per second square. So this is procedure 1 and this is procedure 2. Approximately is 0.1 meter per second square. Approx. Answer is going to be, right, near about, right? Okay. So first you can just calculate the velocity and replace into the third equation of the motion. For that also you have to use that expression of the work energy theorem, right? Or you can use the same expression and replace the value of the work done as F dot D. Then also you are going to get the answers, right? Then also you are going to get the answer. See, you can see now, this is approximately equivalent to 1, right? Approximately it is equivalent to 1. Okay. But in some of the resources this procedure is given, in some of the resources this procedure is given, right? It is mentioned, right, it is mentioned as a constant acceleration, right? So that's why I can say this procedure is best, right? So I'm erasing this stuff. You can directly use this also, but it's not a big deal, right? But this procedure is best because it is given the constant acceleration. Then why to waste our time? Okay. Now A bullet of mass 10 kg leaves the rifle. Right, we are having one rifle like this way, Dishum, right? Okay, a bullet is leaving, right, the rifle at the initial velocity. Initial velocity, that is equal to 1000 meter per second, and it strikes the earth. Suppose the bullet is fired like this way, right? Obviously, the bullet is going to follow the straight line trajectory, but after n amount of the distance, slowly due to the presence of the air resistance, it bends down. The trajectory, right, of the bullet bends down and it strikes to the earth. So when it strikes to the earth, the final velocity is 500 meter per second. Initial velocity was 1000 meter per second. Final velocity was, right, 500 meter per second. The mass that is given as 10 gram. Right, so that is equal to 10 to the power minus 2 kg, right, for the bullet. Now what we need to calculate, the work done in joule for overcoming the resistance of air. It means there is a presence of air resistance. It is resisting the motion. It is opposing the motion. So here I want to write as of air resistance, right, as of the presence of air resistance, the value of the velocity is getting changing from 1000 to 500. That's why the trajectory of the bullet is getting bent and it is going to strike the earth. So arrow as of the presence of air resistance, V changes. And with the change of the velocity, right, the kinetic energy is getting changed. It means that air resistance is doing some work. Why? Because the velocity is getting changed. So here, work done by changing kinetic energy, that is equivalent to change in kinetic energy. Same. Work done by conservative plus work done by non-conservative plus work done by external, that is going to change in kinetic energy. Right. So here we are having only presence of one work done, that is work done by air resistance, and that is going to change in kinetic energy. So work done by air resistance, that is equal to half m V final square minus V initial square. So replacing all of those values, right, we are going to get half into 10 to the power minus 2, right, and that is 500 square minus 1000 square. So we are going to get the work done by air resistance is negative of 3750 joule. Sir, we got the answer as negative. Obviously, if initial velocity is 1000 meter per second, right, final velocity is 500 meter per second, then obviously there is a presence of air resistance, right, into the opposite direction of the velocity, and that is opposing the motion. It is doing some work, right, in changing the velocity of the bullet. Now, in question, it has not been asked what is work done by air resistance. No. How much work is needed to overcome the air resistance? We need to overcome this value. What is work done by air resistance? Negative of 3750, right? In question it has been asked. It is not asked that what will be the right work done by the air resistance. No. What work we need to do, an external agent need to do to overcome this. To overcome this, it means we need to make net work 0. So work done in overcoming, right, that will be 3750 joule. B. Right, very nice question it is. Okay, this question is asked in NEET 2019, and this question is related to motion in vertical circle. And obviously we are going to discuss this thing, right? Okay, when I will discuss, first of all, we will discuss the theory of the motion in vertical circle, and obviously we are going to come to the same question. See, you can see, this is also the same question of a motion in vertical circle it is, right? But it's okay, we are keeping this two question aside. right? And we are going to discuss after the theoretical part of the motion in vertical circle. Now see, we have seen 2 to 3 sums related to it. Now we are going to understand this concepts into the more detailed manner, and we are going to increase the complexity of the sums. Right, now all of the sums will be introduced from my side. Right, suppose all of the sum that will be introduced from my side, right? See, this is an inclined plane, right? Height is 10 meter, particle of mass 5 kg, right? This makes theta, right? There are 2 points, A and B. The question states, when a particle is released on rough surface from A to B, the change in kinetic energy between these two is 100 joule. Mass of the particle it is given. What will be work done by the friction? Clearly it is asked into the question. What is the work done by the friction? A simple question. It's not a big deal. According to the conservation of energy expression, I'm sorry. So can I say work done by conservative, work done by non-conservative, work done by external? The first step we did. According to, see, I gave you all the question solving approach, na? I gave you all that question solving approach, na? You can see, na? This question solving approach. The step 1 we followed. We write down that expression. Right, now we are moving forward to the step 2, check whether there is a presence of external force or non-conservative force or not. Right, so let's see this. Okay, friction is present. Yes, friction is present. The surface is rough. So work done by non-conservative force will be change in potential energy plus, sorry, work done by conservative force will be negative into the change in potential energy. Work done by non-conservative forces, that will result, because as a non-conservative force friction is present, external force is not there, right? So your work done by friction, that is equal to change in kinetic energy plus change in potential energy. What is change in kinetic energy between A and B? 100 joule. So step 2 we did, right? So your work done by friction, that is equivalent to 100 plus U final minus U initial. Now, there are some noteworthy points related to the potential energy. There are some noteworthy points related to the potential energy. What are those noteworthy points? Right, first, potential energy is always calculated with respect to the reference point. It is always calculated with respect to the reference point. It means that, right, suppose this is a ground, this is a reference point, right, and if the particle is at the edge, right, so potential is like calculated like this. At the reference point, potential energy value is always 0. Above the reference point, it is always considered as positive. Below the reference point, it is always considered as negative. At reference point, it is 0. Above the reference point, it is always positive. Below the reference point, it is always negative. It is a choice of student select the reference point. It is a choice of a student to select that reference point. right? Potential energy for a particle, it is always mgh, but if you are calculating the potential energy for a rigid body like chain, right, circular disc, if you are calculating the potential energy for the rigid bodies, right, then this h distance is always between center of mass and reference point, right? This fourth statement is the most important statement, and we are going to use this into the chain problems, right? So this is what an actual concepts related to the potential energy, right? Some of the noteworthy points, as usual, this is a black screen, right? So I'm moving aside, and on the countdown of 5, guys, you can just have a snap of it. 5, 4, 3, 2, 1. So these 4 important steps, guys, we are going to use. Okay. Potential energy is always calculated with the respect to the reference point. Here, the ground is a reference point. Ground is the reference point. Here, potential energy is 0. It means if the object is released from A, it reaches to B. So at ground, the final potential energy is 0. Initial potential energy, obviously, in between the 2 points. Whatever the path you are going to take, no worries. The direct displacement, the direct value of the H we are going to consider. So in between A and B, right, we are not going to consider this. In between A and B, whatever the path you are going to take, the work done will be same. So initial potential energy is this with respect to the reference point. This is mass and this is height. So it will be mgh, right, with respect to the reference point at what height the particle is raised. So what will be the work done by friction? That is going to be 100 minus 5 into 10 into 10. So work done by friction, that is equal to 100 minus 500. So work done by friction, yes, that is equivalent to 400 joule. Why we got the negative answer? Because if particle is moving into downward direction, right, with the component of mg sin theta, we are having the friction that is opposing the motion of the particle. Right, friction is in upward direction, displacement is in downward direction, angle between them is 180. So for that reason we are having what? Right. Okay. In the previous part I told you about, right, into the very previous part I'm showing you all. I'm extremely sorry if I'm taking a couple of minutes, right? We saw the explanation of the work done, right, as a like classification. Work done is positive, work done is negative, right? See this one. If I'm talking about W is equal to F dot D, right? In this I'm considering the vectors. And if I'm talking about F D cos theta, then I'm considering the magnitude. So if this is into the same direction, no worry, work done is positive. If force is trying to oppose the motion, right, then theta between them is 180 degrees. So in that case, work is negative. So friction is acting like into the upward direction, right, and displacement is in downward direction, right. So in that case, right, the work done is 0. Sorry, work done is negative. So for that reason, we got the work done by the friction as negative of 400 joule. Right, work done or by the friction as negative of the 400 joule, right? In this question we got that. Okay, work done by friction, that is equivalent to negative of 400 joule. So this negative sign indicates, right, this negative indicates angle between friction and displacement, that is 180 degree. Next sum. This was a very simple explanation, very simple sum, right? Now let's move on to the different. From the height of 10 meter, from the height of the 10 meter. Particle is released. Mass is 5 kg. Here, we are having one spring attached, having spring constant K. If, see, entire path is smooth, a particle we are releasing from the topmost part, right? It is going to slide down onto the smooth part, right? And finally it is going to compress the spring of the spring constant K. So in this case, right, what will be the maximum compression in spring? Same work energy theorem we are going to use into the same method. Steps, right? First of all, we need to select the reference point. This will be the reference point ground where potential energy will be 0. Step 1, right? Work done by conservative, work done by non-conservative, work done by external, right? All will result in changing kinetic energy of the particle. Right. Step 2, check the presence of the friction. All surfaces are smooth. So, step 2, the work done by conservative will negative change into the kinetic energy. Friction is absent. External force is absent. Right. So, it means that directly delta K plus delta U is equal to 0. U initial, the total energy and the initial and the final points are constant. This is the initial point. What is the final situation? Ball reaches like this way and compresses the spring. This is the final situation. So at initial, what is the summation of kinetic and potential? At final point, what is the summation of kinetic and potential? We have to evaluate that. So at initial, particle is just released. Means velocity is 0, kinetic energy is 0. At this point with respect to the reference point, what is the potential energy mgh? It is phi into g into 10. So at initial position, right, we wrote down the summation of kinetic and potential. When spring is compressed, fully compressed, at that moment of time, obviously this particle is going to be at rest. Whatever the potential energy particle is having, it is going to convert right into the respective kinetic energy at the bottom of the surface. And that kinetic energy, right, see, whatever the see, I'm reframing my statement. Whatever the gravitational potential energy was that, it was fully converted into kinetic energy. No energy loss is considered. And this kinetic energy that particle attained, it is going to convert entirely into elastic potential energy. Gravitational potential energy to kinetic, kinetic to elastic potential energy. So finally, when the spring is fully compressed, only we are having elastic potential energy, not the kinetic energy. So final kinetic energy will be 0 and this will be half kx square. Right? So this is, we are having phi into 10 into 10, that is equal to half kx square. Right? So this is 1000 is equal to kx square. X is equal to under root of 1000 by k. Right? This is what the maximum compression into the spring is. I haven't taken the value of k because this question is framed by myself, right? So that's why I have not taken the value of the k, right? But the most important stuff is an explanation. See, you can identify, right, how deeper we are going into the roots of the concepts, right? See, from this point. Simple, first of all, we use a simple equation, right? A very simple, this was a question solving approach. We use a very simple equation, right? After that we moved on, okay, to this part, right? The first sum, the simple sum. After that we moved on to the, right, the springs are somewhat involved. Right, now let's move on to the another sum. See, this is also the nice one. Right, we are going to solve some 8 to 10 sums related to the work energy theorem, right, and you are really going to enjoy, right? From the height h, spring was already concept and work was already done in compressing the spring. Step 1. Work was, right, previously done in compressing this spring. Now particle is kept and released. Particle is kept and released. Up to what horizontal distance from the bottom, right, it will strike the ground. Up to what horizontal distance it is going to strike the ground. See what it states, all surfaces are smooth. Mu is 0. Here also mu is 0. Previously, right, work was already done on the spring, right, while compressing it. And after maximum compression, particle was placed in front and released. Dadang. So it means that obviously step to step we are going to solve it. Work done by non-conservative, work done by conservative, plus work done by external, all will change into the kinetic energy of the particle. Step to step, same procedure we are going to follow. Second, is there any presence of the non-conservative or friction? No. Work done by conservative, negative change in kinetic energy. External forces also absent, mechanical energy is conserved. It means initial kinetic energy, right, initial potential, final kinetic energy, final potential. I am taking this as the reference point, right? Okay. Why I am taking this as a reference point? But because at this position, right, everything is going on to the same surface level, right? Everything is going on with the same surface level. So all the terms of gravitational potential energy will get nullified. It is also important to select the correct reference point. If you are selecting the wrong reference point, now that can increase the terms into the equation. But if you are selecting this reference point, now because everything is, by selecting this reference point, everything is going on to the same surface level. So it means what? All of the terms of the gravitational potential energy will get nullified. So here initially particle was at rest, it was just released, kinetic energy was 0. At initial position, spring was compressed, it means work was done on the spring, and that was half kx square. After it is released, right, whatever the, right, see, after it is released, the potential energy will be 0. Why? Because the spring is released completely. It means that it will be again back, it will move back to its original position, its natural length. And in natural length, no elongation, no compression, no work done. So right now it is facing the maximum compression. After it is released, right, ball will move like with this way, right, with the constant velocity v. And in that case, the spring will be in nature. When the ball is fully, right, relieving itself from a spring, the spring will be in its natural length, position of the natural length, and in that case work done is 0. So final potential energy work done is 0. Sorry, final potential energy will be 0. Final, obviously it is a smooth surface, so it is going to gain the constant velocity half mv square. So what will be the velocity of the particle under root of k by m into x? Equation number 1. Now, second, spring in its natural length, this is moving with the constant velocity, and this velocity is also not going to change because the surface is smooth, right? So whatever amount of the kinetic energy received, right, okay, from this, it is going to have the same amount only. It is not going to change. Now at this point, it is having the horizontal velocity. It is projected with the horizontal velocity. So in this case, it is going to follow the horizontal projectile motion. And this will be the range of the horizontal projectile motion from height h. So what is the equation of range? R, that is equal to velocity. It was released into under root of 2h by g. What was the velocity? The horizontal velocity after getting released from the spring. Particle was having under root of k by m into x. So this is under root of k by m into x into under root of 2h by g. Right? So what will be the range? Range will be under root of 2hk by mg into x. This is the range of the particle. Up to this distance, it will fall, it will strike on the ground. See, you can see how we use the concepts of work energy theorem and the horizontal projectile motion to solve this sum. Right? To solve this sum. You can replace the value. The important thing is how to apply this concept. Right? We are not interested in values. Values will be given into the question, whatever the stuff you need, right? It will be mentioned, right, in the data. But the most important thing is to how to apply this, right? So this was this next question. Now let's move on to the another. This is very nice. This is a fixed wall, the rigid wall. Mass m, it is moving with the v meter per second velocity. Here spring is there, right? Surface mu is 0. Mass m is initially moving with the velocity v, right? Initially spring in its natural length. Right? Suppose it is moving, obviously it is going to collide with the spring, right? So what will be the maximum compression into the spring? Slowly I'm going to increase the complexity. First of all, you are going to solve this, right? After we are going to solve, right, after this sum, we are going to include the conservation of momentum. Slowly, lots of things we are going to discuss, right? But at the end of this, right, we are going to clear the concepts of how to apply the work energy theorem. It is important. The concept of how to apply is important. So obviously, work done by conservative, work done by non-conservative, plus work done by external, that is equal to delta K plus delta U. Step 1. Select the reference point. The reference point would be this, right? And everything is going at the same surface level. So all of the gravitational potential energies will be 0. Is there any presence of the conservative forces? Yes. That is equivalent to change in potential energy. Non-conservative and externals are 0. So delta K. Finally, we are going to reach the third step. Mechanical energy is conserved. Right, so the total energy is constant at the initial and the final points. Initial spring is at the natural length and everything is going at the same surface level. So potential energy is 0. Particle of mass m is moving with the velocity v. So kinetic energy is half mv square. Finally, spring is get maximum compressed. So particle will be at rest. Final kinetic energy is 0. Everything, see, this potential energy is resultant of gravitational and elastic. Everything is going to be at the same surface level. So gravitational potential energy will be 0 and elastic potential energy will be half kx square, right? So finally the maximum compression into the spring we are having as, right, mv square, that is equal to kx square, x that is equal to m by k, right, under root of v, right? This is the max compression in spring. Maximum compression in spring. A very simple sum. You can see, first of all, I show you all this concept, right? How, right, in between A and B, right, the friction is doing work. After that, I released the friction, right, and we saw how the spring was getting compressed. After that, right, we saw this sum, how a spring was already compressed, and we combined the work energy theorem with the projectile motion. After that, we saw this sum. Simple. Now, boom. Initially, m was moving with the speed of v meter per second. Let's take an example. It was moving with the u meter per second, right? I think it will be easy using this terminology. Initially, it was moving with the u meter per second. Now, in previous question, right, there was a rigid wall here. Here, I have kept the free surface. We are not having any kind of the rigid wall. It's a free surface. M is initially moving with the u meter per second. Suddenly, spring is in its natural length, right? M is moving, spring in natural length. Suddenly, M collides with this, and spring is get compressed. Now the both systems are moving with some velocity. Very interesting question. So what will be the maximum compression in spring? The same procedure we are going to follow for this. All the surfaces are smooth, right? Mu is 0, right? And obviously we are going to take the reference point as the surface level. First of all, right, okay, just analyze what actually the things are going on, right? This is initial situation. What? M is moving with u, spring it is in natural length, and 3m is attached to it. Here the velocity is 0, spring it's in natural length, x is 0. So this is the initial situation. What will be the final situation? The mass m got struck with the spring, it compressed the spring, right? So it means whatever amount of the kinetic energy it was possessing, right? Some of them it got converted into the elastic potential energy. Initially he was having the kinetic energy of half mv square, right? Now this m and 3m, they both are combinedly moving with the velocity v, and spring is compressed with half kx square. This is the final situation. Initial situation was m was in its nature, m was moving with u meter per second, the spring was in its natural length, and even 3m was 0. slowly it came nearer to the spring. Spring is a helical structure. Slowly it got compressed. After maximum compression, still m is having some amount of the velocity. So what will happen after maximum compression? Obviously both will start moving with the common velocity. They both are moving with the common velocity. This is the final situation of the system. So in between initial and final, how we are going to apply the conservation? First step, right? Okay, how we are going to apply the conservation is a very simple step. See, work done by conservative plus work done by non-conservative plus work done by external, right? That is equal to changing kinetic energy. Everything smooth, everything is there, right? So we are directly going to use delta K plus delta U is equal to 0. Initial kinetic, initial potential, final kinetic, final potential. Initial kinetic energy. M was moving with U square. Initially spring is its natural length and everything is going on into the one same surface level, so potential energy is 0. Final kinetic energy, m and 3m, they both are moving with the common velocity v, and spring got compressed with half kx square. So this will be half is got cancelled, m u square, that is 4m v square plus kx square, right? So this m is also no, m will not get cancelled, right? M will not get cancelled, right? So this will be m u square minus 4m v square whole divided by k is equal to x square. Still we are not having the value of v. If in one equation, right, we need to find the maximum compression in spring. So for that we need one unknown. Suppose value of u is given. Still in this expression we are having two unknowns. The final velocity of the system we are not aware of. Now if I'm talking about the entire system, momentum is conserved because external force on the system is 0. The net external force on the system is 0. So it means initial momentum that will be equivalent to final momentum. Initial m was moving with u. Finally m plus 3m both are moving with the velocity v. V will be u by 4. Jackpot. Bingo. Replacing 2 in 1. Replacing 2 in 1. So what we get? Okay, we get this as m u square minus 4m v square, that is u square by 16 whole divided by k is equal to x square, right? Now m u square we are having, this is constant, this is 1 minus 1 by 4 is equal to x square, this is 4, right? So this will be 3m u square by 4k is equal to x square. So x will be, right, u by 2 under root of 3m by k. This is maximum. See now, m is known, k is known, u is known. In this expression we were having two unknowns. In this expression, right, suppose the value is given, right, then we are having only one unknown, and that is the maximum compression into the spring. This is how energy conservation is applied, right? If you want to have a snap of it on the countdown of 5 seconds, right, on the countdown of 5 seconds you can have a snap of it, right? Come on, 5 4 3 2 1. So this is all what about the conservation of energy. Now the same concept we are going to solve, the same concept, right, we are going to use, right, for the chain problems. Now what actual the chain problem is, what actual the chain problem is, right? Till now we have seen the sums in which particle was involved. Now we are going to see the sum in which rigid body is involved. What will be the question solving approach? Simple. Work done by all forces, that is equal to change in kinetic energy. Work done by conservative, work done by non-conservative, work done by external, that is equal to change in kinetic energy. Work done by non-conservative plus work done by external, that is equal to change in kinetic plus change in potential. Step 1, use this expression. Step 2, check the presence of a friction and the external forces. If not, then follow the procedure, right, of the mechanical energy conservation, in which between initial and final point total energy is constant. And if not, there is a presence, you have to use this expression. This is only the question solving approaches. Now, we are having a dome. Right? Of radius r. Semicircular dome. Right? There are 2 points, point A, point B. Initially, chain is at rest. Initially, the chain is at rest. Suppose a gentle push is given at B. This chain will slide down. So what will be the velocity of the chain at B? Surface is smooth. Right? Surface is smooth. This kind of the chain problems are there. We are going to see some 2 to 3 chain problems, and obviously we are going to get this stuff easily. First of all, we are going to see this sum. After this, we are going to take the semicircular chain. In both of the cases, right, friction will be absent. The third case we are going to see, in which there will be the presence of friction. Right? You are going to see, you are going to enjoy it a lot. Now, mu is 0. It means we are not having, see, same procedure we are going to follow. Work done by conservative plus work done by non-conservative plus work done by external, that is equivalent to change in kinetic energy of the particle. Right? Okay, that is equivalent to change in kinetic energy of the particle. I must say yes. Okay. No, this is not true. I'm sorry, this is wrong. This is only change in kinetic energy. Right? I'm sorry, this is wrong. This is the correct. Okay, this equation is only equivalent to changing kinetic energy. After that, the conservative, whatever the work is done by conservative force, it is going to add on to the opposite side. So let's check it all. This is the correct. Right? In the last question, we only, this is also correct. Right? In last question, we only did a mess. It's okay. It's not a big deal. Right? Now, friction is absent, everything is absent. It means delta K plus delta U is equal to 0. What will be the reference point? This will be the reference point where potential energy is 0. Right? Now, initial, final, this is the equation. So, initial situation is like this way only. The chain is at rest. Right? Chain is at rest. It means kinetic energy is 0. What about the potential energy? See, this is a rigid body. In the previous cases, you can see, right, in all of those previous cases, right, particle was involved. Right? So we were not dealing with any kind of the densities, or we were not dealing with the structure of particle, the configuration of the particle. But in this question, right, we are going to deal with the configuration of the particle. It is a chain of the semicircular, what you can say, it is a chain of length L, and it is lying on the semicircular dome. For a semicircular arc, remember, right, when I was writing down some of the noteworthy points related to the potential energy, whenever you are dealing with the particle, it's okay. But whenever you are dealing with the rigid body at height, whenever we are dealing with the rigid body at height, the distance between the reference point and center of mass of the rigid body is considered. Right now, see, actually the students are having misconception, right? Okay, that potential energy of the chain should be mgr. Wrong. Why? Because chain is not at this much point. It is uniformly distributed on entire dome. So in that case, right, the concept of center of mass is specially introduced for the rigid bodies, in which what we used to consider, the mass of the entire chain is concentrated at the single point, right? That is center of mass, and distance between that reference point and center of mass is considered. This is an actual concept, right? We are shrinking the mass of entire chain to an imaginary point that is its center of mass. Now, see, while analyzing the chain, it's okay. But when you are analyzing the center of mass, the mass of the system gets concentrated at single point. Now, the particle is this, right? And the distance between the reference point and center of mass is h. For a rigid body, this spatial treatment we need to give. So what will be the potential energy? It will be not equivalent to mgr. It will be mgh. H is the distance between, I'm writing here, h is distance between center of mass and reference point. Finally, chain comes like this way. After having the gentle push, chain comes like this way. The length of the chain is this, L. Now the center of mass of the chain is at this position. Obviously, when it is gently pushed, it slides down. Obviously, it is going to have some velocity at the point B. At the point B. But at this point, what will be the potential? It is a rigid body, not a particle. And it is not at the reference point. What I told you all, above reference point, potential energy positive. Below reference point, potential energy is negative. So here we are going to get the negative potential energy. Same, it is a rigid body, distance between the center of mass and the reference point is considered, right? So it is a negative of mg, right, L by 2, right, L by 2, right? So we are going to resolve this sum. mgh, that is equal to half mv square, right, minus mgl by 2, right? Lots of unknowns are there. M we are going to get cancelled. 2gh is equal to v square minus g of l, right? Now what is an actual length of the chain? Half of the circumference of the circle, pi r. Circumference of the circle, 2 pi r. Half of the circumference of the circle, pi r. What is the length of the chain? Pi r. So can I replace it instead of L? Can I write it as pi r? Yes, I can. So what will be the velocity at B? That is equivalent to 2gh minus g pi r, right? Okay. We are not aware of the value of, right, h. Okay. So VB, that is equivalent to taking g common. It's 2h minus pi r, right? We are not having the value of the h, right? But it is a standard data. right? It is the standard data. What is the standard data? That thing we are going to see into the right concepts of center of mass, right? But for now, I'm going to show you all, right? You have to just accept the standard data at this distance. If it is a semicircular disk, then this distance is 4r by 3 pi, right? So again, I replace this value of h as 4r by 3 pi. So it's 2 into 4r by 3 pi minus pi of r, right? Okay, so this r is square, vb square, that is equal to gr 8 by 3 pi, right, minus pi, right? So what will be the velocity at b? That is under root of gr 8 by 3 pi minus pi. This is how chain problems are resolved, right? This thing we are going to see, you have to just accept it right now. We are going to see into the next part, into the next session. You have to just accept it right now. Okay. Now, like this way, right? Second sum. If it is a semicircular disk and chain is lying like this way, right? The center of mass shifts to like this way. This will be also h and this will be also h, right? Its concept of the center of mass is simple. If this is a full disk, right, center of mass is at the center. Okay, suppose if half of the thing is removed, right, half of the thing is removed, then center of mass shifts to the heavier side, right? Suppose if another half is also removed, right, suppose if another half is also removed, right, then again the center of mass will shift to this side. In that case, this is also h and this will be also h. This thing, everything we are going to discuss into the concepts of center of mass, right, and all of those derivations, right? So this thing is a homework from my side. You can solve this, right? This is point B. We need to calculate the velocity at the point B, right? We need to calculate the velocity at the point B. You can do that, right? This is h comma h, the new center of mass. So this is a homework from my side, and the answer for this question, right, you need to you need to answer this beneath the video into the comments. I will be waiting for all of those. Now till now, right, we haven't considered the friction, but I'm showing you all another example. L by 2, right, mass m by 2, okay, this is smooth, this is having the friction. Suppose if suppose, right, okay, what will be the work done by external force, right, so that this chain can come like this way? Or in another sense, what is an external force, right, needed, okay, so that this chain can be pulled like this way entirely on the horizontal surface? This is an initial situation, right? This is a final situation. What work an external agent, right, does, okay, to pull the entire chain from this to this situation. So this is also the homework from my side, right? Okay, this is a chain problem that includes the friction, right? This is also the nice sum. So this was all about the conservation of energy, right? Now in this, right, the two most important concepts are remaining, right? The first one, that is a motion in vertical circle, and second, that is a collision, right? So immediately we are going to see all of those stuff, right? Okay, so are you all ready? Let's move on to the concept of the motion into the vertical circle. Motion in vertical circle, right? The most of the important application of work energy theorem, right? The most important application of the work energy theorem. What it states, what is an actual concept, right? Which two formulas are going to, we are going to, like, it will be quite helpful for us, right? Let's see this. Okay, now see, motion in vertical circle. The actual concept states that an object of mass m, it is tied with a string like this way, right? Suppose let's take a very simple example that I am having in front right now. Okay, let's have this, right, to understand the concept very well. Okay, it's done, right? Okay, see, object is like this way, right? Suppose it is released from the bottommost position with the horizontal velocity like this way. It is released, right? Okay, suppose at the bottommost part the u velocity is given and it is following the vertical circle like this way. This activity, right, this whatever the phenomena it is going on, it is known as motion into the vertical circle, right? Motion into the vertical circle. Now, what is an actual concept? The actual concept, it is one of the applications of work energy. Two most important questions: variation of tension, right? Variation of velocity, right, with respect to the angle theta, with respect to vertical or the bottommost far from where the particle is projected, right? The minimum velocity needed to complete the vertical circle, right? And some of the conditions related to it. This all of these things we are going to discuss, right, for the motion into the vertical circle concept, right? This all of these things, right, we are going to discuss for the motion into the vertical circle concept. Now, first of all, let's move on, right, to the equation of velocity. Suppose from the bottommost point, particle is given the velocity as u meter per second, right? Obviously, it is following the vertical circle like this way, right? Is following the vertical circle like this way, right? Now, how the velocity is changing, right, with respect to the angle theta. Suppose at the bottommost velocity we are having u, particle is at this position, the position of the particle is changing on the right vertical circle. So how the equation of the velocity we are going to define it? Suppose this is the point that is making angle theta with respect to the vertical, right? That is making angle theta with respect to the vertical. Okay, so in this case, so what will be the variation into the velocity? Sorry, right? Suddenly I received a call. Extremely sorry. Right, lots of things are going on. That's why, right? The new surprises are going to come. Okay, so don't get worried. They are all like good things for you. Okay, very good things. Okay, so you suppose at the bottom it is released at the u meter per second. So at this point, right, obviously it is going to have velocity v. So with respect to theta, how we are going to identify the relations between u and v? Same work energy theorem we are going to use. Step 1, this will be our reference point. If you want to take this as a reference point, it's okay. If you want to take this as a reference point, it's okay. But by taking this as a reference point, one term, one expression of the potential energy on the either side will get increased, right? At the end, it is going to cancel out, it is going to nullify, but we have to write it down. So it's good to take the reference point, this as the reference point. So this is an initial position, right? And this is the final position. So can I say there is no resistive forces, right? No dissipative forces are present. So immediately the energy is conserved. The mechanical energy is conserved. So at initial, potential energy is 0. Kinetic energy we are having half mu square. At final, right, with respect to the reference point, suppose this is a reference point, particle is like this way, right, making some angle theta. So can I say this is L cos theta, right? This is L cos theta, right? This suppose this is L, this is making 90 degree. So this is theta. So this will be L cos theta, right? But with respect to the reference point, we need this height. So can I say that is L minus L cos theta, that is L1 minus cos theta, right? So the final, it is half mv square plus mgl1 minus cos of theta, right? So rearranging this term, we are getting v square, that is equal to u square minus 2gl1 minus cos of theta, right? So the variations of the velocity, right, okay, or the velocity at any point, it is given like this way. This is the equation. Can I consider this is equation number 1? Yes. At the same point, we are going to discuss what is the minimum velocity needed so that it can complete the vertical circle, right? Minimum value. Okay, first of all, let's move on to the concept of tension first, right? Now, how the variations of the tensions we are going to determine in this case. Same. At the bottommost point, u meter per second, it is given. It is completing the vertical circle, right? Now, between point A, right, and point B, how tension is getting varied. Between point A and point B, how the tension is getting varied, right? How the variations of the tensions are taking place, right? How? It's a very, very, very simple thing. Okay, now let's move on. At the bottommost point, can I say tension is acting into the upward direction, mj is in this direction, and mv square by r centripetal is in upward direction. While, sorry, mu square by r. While at this point, tension is in this direction, right? Centripetal mv square by is in this direction and mg cos theta is in this direction, right? So suppose if I want to use the Newton's law at the point B, can I write the net force is centripetal force mv square by r, right? That is equivalent to T minus mg of cos of theta. So tension at that point, see, tension at any point that is changing with respect to theta, that can be given as, this is the reference point, okay, theta is calculated with respect. So tension is equal to mv square by r minus mg of cos of theta, right? Can I consider this is equation number 2? Yes, this is equation number 1. Can I replace equation number 1 in 2? Replacing equation, right, 1 in 2, what we get? Replacing equation 1 in 2, what we get? T, that is equal to m by r, right? U square minus 2gl. L you can consider it as a r. L and r both are the same thing, right? L, R both are the same thing, right? It's okay. So m by r, that is u square minus 2g r1 minus cos theta. Minus mg cos of theta, right? So this is mu square by r minus 2 mgr by r 1 minus cos of theta, right? And that is again, this is minus, right? So it is minus mg cos of theta, right? Solving this, we are getting t is equal to mu square by r. This r is going to cancel, right? Okay. And okay, 1 minus cos theta, minus minus is going to be plus. So this is minus 2 mg, right, plus 2 mg cos of theta, right? Okay. Sorry, this is plus. I'm sorry. This is plus. I'm extremely sorry. This is plus. And that is plus mg cos of theta. This is plus. Because this is moving on to this side, we are getting it plus. Sorry. So t is equal to mu square by r minus 2 mg plus 3 mg cos of theta. So the final equation of tension, we are getting mu square by r minus mg 2 minus 3 cos of theta. This is how tension is varying with respect to the bottommost point and angle, right? This is how velocity is getting changing with respect to the bottommost point and the angle. Suppose this is the equation of the tension we need to use. Suppose if we need to calculate the variation, see on the vertical circle, right? If you need to calculate the variations of the tensions between A and B, simple, right? Tension at A, right? Suppose this is our reference point and with respect to this we are calculating the theta. So at this theta is equal to 0 degree. So it's mu square by r minus mg, right? 2 minus 3 cos of theta. Cos is 0. So tension of A is mu square by r minus mg, right? 2 minus 3 cos of 0. Cos of 0 is 1. So tension at A, that is mu square by r minus mg, right? And 2 minus 3 is minus 1, right? Cos of 0 is 1 na, so 2 minus 3 is minus 1. Minus minus will be plus. So tension at A, that is equal to mu square by r, right? Plus of mg. Can I consider this is equation number 1? Yes. Now, how to calculate the tension at B? Because we need to calculate the difference between them, na? Right? So TA, TB, right? That will be again mu square by r minus mg 2 minus 3 cos of theta. Suppose if I'm talking at B with respect to A, angle is 180 degree. Unnecessary, again and again we don't have to apply the conservation and we have to apply the Newton's second law. No, we are having the direct equation, we can use that. So TB, that is equal to mu square by r minus mg cos of 180, that is equal to 5. This is minus 1, this will be 5 mg. So TB, that is equal to mu square by r minus 5 mg. The tension between B and A, right? Or sorry, in between A and B, I'm sorry. Okay, tension between A and B, how to calculate? Simple, we are having the two equations in front, right? So TA, that is equal to mu, sorry, TA minus TB, okay? I'm sorry, TA minus TB, right? We are going to get the difference, okay? TA minus TB, that is equal to mu square by r plus mg minus mu square by r plus 5 mg, right? This is gonna cancel. TA minus TB, we are going to have 6 mg. This is a tension difference between the 2 points on the vertical circle with respect to the reference point, that is the bottommost. Like this way, you can calculate you can take any reference point. It's not a big deal. You can calculate the tension difference between any 2 points. Suppose if you want to calculate the tension difference between A and C, at A you have to replace the angle as 0, at C you have to replace angle as pi by 2. Right? So this is how the variation. Similarly, if you want to calculate the velocity difference, we can calculate. Right? By void formula, we can calculate by using this. At the bottommost point, you can replace the theta, At the topmost point or else point, you can replace the theta. Now, in the motion in a vertical circle, this was the equation of the tension. Right now, what is the minimum velocity required? Right? Okay. Suppose, what is the minimum velocity required at the bottom, right, so that it can complete the vertical circle? To complete the vertical circle, obviously we need that much amount of the velocity so that it can reach up to top. At the top, tension is in this direction, mv square by r is in this direction, right, mg is in this direction. So at the top, right, tension will be completely zero. So can I replace the equation of the tension, that is mu square by r, right? Okay, mu square by r minus mg 2 minus 3 cos of theta. We need to apply the enormous amount of the, we need to apply, right, the needed amount of the u so that it can just touch the, it can just reach the topmost part of the circle. It can just reach to the topmost part of the circle. So at the topmost part of the circle, theta is 180 degree, and at the topmost point, tension will be 0. That is mu square by r, that is minus 5 mg, right? So u, right, minimum needed 5 gr, right, for particle to reach top or complete vertical circle. If you are applying minimum under root of 5 gr at the bottommost point, it is going to reach at the top also, and it is going to complete the vertical circle. In some cases it differs, but generally we are taking this term. So what is the minimum? Minimum velocity needed, that will be equivalent to under root of 5 gr. Minimum velocity needed, that is equivalent to under root of 5 gr. Okay. Now, question solving approach. First, equation of the velocity v is equal to under root of u square minus 2g L1 minus cos of theta. Second, variation of the tension, that is equal to mu square by r minus mg 2 minus 3 cos of theta. Right. Minimum velocity needed, that is at the bottommost point under root of 5 gr. Right. Okay. Yeah, and apart from this, lots of things are there, right? How much minimum velocity is needed? Suppose this is point A. How much minimum velocity is needed to reach the point A? Just reach under root of 2g. How much minimum velocity is needed so that it can cross point A? How much minimum velocity is needed right at the bottom, so it can be in between A and B? That table is there. U under root of 2gr, under root of 3gr, under root of 4gr, and lots of resources, many things are there. But according to me, you have to just remember two things. At the bottommost point, if you are applying under root of 2gr, it is going to reach at the point A. Just to reach at the point. If you need just two things, you should remember. If you want that this particle should reach at the topmost point of the circle, minimum you need to apply it under root of 5gr. And if you want that it should reach point A, minimum at the bottom you should apply it under root of 2gr. Apart from this, suppose here the value needed is 2gr under root. Here value needed is under root of 5gr. So in between this two, right, variations will happen. In thousands of the resources, thousands of variations are given, right? And students always, oh, this table is quite important, and they used to mug up and mug up. No. Just simple two things. Under root of 2gr, you know, to just reach here, and under root of 5gr to just reach at the topmost point. Right? Now, this is the concept of the motion into the vertical circle. Now we are directly, right? We have left two sums of the this work energy theorem that was completely based on the motion in the vertical circle is application, this one. Yes. A mass m is attached to the thin wire and whirled into the vertical circle. The wire is most likely to break when, right, at what point into the vertical circle, see this question is asked in 2019 NEET examination. At what point into the vertical circle we will have the maximum, sorry, the wire is, right, will get breaked. The maximum amount of the tension that is generated into the, produced into the wire will have the maximum possibility to get break. So suppose at the bottommost point, tension is like this way, right? And here it is mg and here it is mv square by r. So at point A, if I am applying the equation, we are having mv square by r, that is equal to t minus m of g. So t is equal to mg plus mv square by r, right? This is what happening at point A. If I'm talking about the topmost point, right, mg into downward direction, centripetal into downward direction, tension into the downward direction. So at B, mv square by r, that is t plus mg, right? So t is equal to mv square by r minus mg. You can see the difference between A and B. At A, tension is more as compared to B, and obviously at the other points, right? Okay, at the other points, obviously tension is going to differ. Here we are having t is equal to mv square by r, right? So obviously we are having only 2 points to analyze, the bottommost point and the topmost point. And in between the bottommost and topmost point, even you can see, right, at position A, we are having the maximum amount of the tension. So in that case, if we are having maximum amount of the tensions, and there is only the possibility at that point only the string can break. It is just a lowermost point. When the mass is at the lowermost point, the tension is more. The tension is more, there is a highest possibility for a wire to get break. Right? There is a highest possibility of a wire to get break. This is a release from the top. Now see, this question is asked in NEET 2018. This is a release from the, first of all, let's determine the reference point. This is a reference point where potential energy is 0. This is a release from the top. Now it is reaching at the bottom. From what height it should release? See, a body is initially at rest, sliding down the frictionless track. Friction is not present. It means from work energy theorem, mechanical energy is conserved. Directly we can use this equation Ki ui Kf uf. Between the initial and final points, total energy is constant. From what height it should released so that it should complete at the bottom. From what height it should released so that it can reach at the bottom mass part and complete the vertical circle. This is an initial point, right? Let us consider this as a final point. In between initial and final, let's apply the energy conservation. K initial, U initial, right? K final, U final. At initial, it is just released. So kinetic energy is 0. At initial, we are having potential energy as mgh, right? By reaching there, we are having kinetic energy is half mv square, and we are reaching right to the reference point, so the potential energy is 0. So here v square, that is equal to, right, 2gh. After reaching the bottom, right, we are having the velocity as under root of 2gh. But to complete the circle, how much amount of the velocity we needed at the bottom? At the bottom, we are having under root of 2gh. But to complete the vertical circle of radius r, right, we need under root of 5gr minimum velocity, right? So to complete the vertical circle under root of 5gr, r means d by 2, we need r. They have asked in diameter, that's why. This much amount of the velocity is needed, right? This much amount of the velocity is needed. But at the bottommost point, we are having under root of 2gh. There is issue. Needed velocity is this, but we are having this. So it means if you want to complete that vertical circle, this two should be equal. So evaluating this, you are getting h as 5d by 4. D is the perfect answer. If it is released from 5d by 4, it is going to come down and complete the vertical circle. NEET 2018. So these were the two questions, right, that we saw. Now we are going to move on to, okay, chain. Again, NEET 2016, phase 1. What is the minimum velocity with the body mass m must enter the vertical loop? Simple. Bottommost point minimum velocity needed, right? So at the topmost point tension should be 0. Mu square by r minus mg 2 minus 3 cos of theta. We need to find the value of u, right? So at the topmost point tension is 0. So 0 is equal to mu square by r minus ng at topmost point. Cos is 180, right? So you are getting u minimum as pi gr. Simple. NEET phase 1 2016. This is a homework from my side. This is also the nice sum. This is based on the equation of the velocity that we discussed right now, right? So I will be waiting for our answers here beneath the video, right? I will be waiting for this answers right beneath the video. Okay, now. As shown into the figure, the particle mass is performing the vertical circular motion. Average velocity of the particle at which point string will break. We are having only, we discussed at the bottommost point tension, we are having T is equal to mv square by r plus mg, right? While at the topmost point, right, we are having that is mv square by r minus mg. So there is only one possibility that at the bottommost point, right, okay, this tension may get maximum and the string may get break. Okay, this was the concept of the motion into the vertical circle. See now, power, right? Power is not as much exaggerated that what we are, right, having impression. Power is having some simple terms, 1 to 2 terminologies, right, and the things get over, right? Just 1 to, I'm extremely sorry about that, just 1 to 2 terminologies and things get over, right? Just 1 to 2 terminologies and things get over. Power. Miss Marvel. Miss Marvel. Miss Marvel. Miss Marvel. Power, if you want to, right? The time rate at which work is done. The time rate at which work is done. Very simple explanation. If I am see, 2 students are present in front, right? I am giving a task to both of them. One has to complete 2 chapters, right? Okay, in 2 hours of time. The second has to complete 4 chapters, right? Okay, both are given the common task that they have to complete the 2 chapters in 2 hours of time. Oh, brutally that's not possible, but I'm giving you an example to understand this stuff, right? One is completing, right, 1 chapter in 2 hours. Second is completing 1.5 chapter in 2 hours, right? So who is doing more work? Who is doing more work? Let us take another example about it, right? Okay, one fellow, right, okay, is trying to vacate that truck in 5 hours of time, and another fellow is trying to vacate that entire truck in 8 hours of time. So who is doing more work? Who is taking less amount of the time? The person who is taking 5 hours of time to vacate that entire truck, right, he's doing more work, right? Mechanical work right now, not any abstract thing is going on, right? We are only talking about the mechanical work. Similarly, the time rate at which work is to be done. Power dW by dt. If you are replacing, right, it as F dot D, and if force is constant, right, Fx, right, then P is equal to F dx by dt. Another formula is P F dot V. This is a dot product now, right? Okay, this is what actually the power is, right? Lots of things related to the power are asked, right? It's okay, but it's not a big deal. Okay, this is what simple the power is with the visualization with Miss Marvel. Extremely sorry for, right? Yeah. Okay, so these are sums, right? They had been asked, right? They're very simple sum. Everything is based on the one simple formula: P is equal to dW, right, by dt, and that is equal to F dot V, right, and that is equal to M dV by dt into V, right? Okay, this is only the thing that this is only the formula for the power and question solving approach, right, guys? So this thing you can do, it's not a big deal, right? Okay, this thing you can do, it's not a big deal. Okay, now last part of this chapter, and that is collisions. Collisions we can discuss with the center of mass also, but I want you all, right, okay, to discuss in this chapter only, because a lot of things related to this we have seen. We have seen to the conservation of energy, we have seen the velocity variations, right? So whatever the factors in this chapter we have seen, this thing we are really going to help in this understanding this collisions, right? So let's move on to this part of collisions. Okay, so let's understand this stuff. Collisions, right? Okay, see this thing again, right? It will be right with the center of mass, right? The 2D part will be repeated. It's okay. Okay, but this collisions, right? I think it is going to help a lot. Okay, so collisions means what? A very simple example, right? Okay, see, till now we have seen what is work, what is energy, some of the concepts related to the work energy theorem, and lots of examples related to it, right? Some of the concepts of the power and blah blah blah, right? Motion in vertical circle. Now this is a very small concept that is remaining, right? Okay, collision, its classification, its nature, type of collision, and 2 to 3 formulas are there, not more than that, right? 2 to 3 formulas are there, not more than that. See, collisions means what? Right? Accident of car and truck. Collision. Slap. Collision. Right? Have you ever played that carom? Right? It's one of the example of the collisions, right? So whenever the two, right, bodies interact with each other, right, interact with each other, I must say they are colliding in any way, right? The best example, Jeff is in front. There is no, like, lots of technical definitions and thousands of resources are there, right? But we are not going on to that much detail. The collisions, it means, right, two particle interaction. Okay, two particle or two object or two rigid bodies interaction. That's it. Okay, see now. There is a difference. There is a difference. Accident of a car and truck, it is different, right? While playing a carom, right? While playing a carom, if the striker strikes, that collision, it is a different. While playing a pool, when two billiard balls collide, that collision is different. So there exist many types of collision. There exist many types of collisions. How to identify the nature of the collision? For that, we are having the most important term, that is coefficient of restitution. the coefficient of restitution defines, right, whether the collision is elastic, inelastic, plastic, right? Okay, so before moving on to the this nature of the collision, let's move on to the first of all the classification of it. First, elastic collision, right? Inelastic collision, right? Perfectly inelastic collision. Elastic collision, right? Inelastic collision, perfectly inelastic collision. Elastic collision, inelastic collision, perfectly inelastic collision. Then how am I able to differentiate that? Collisions offers true billiard balls, right? There is no energy loss. And if I'm comparing that example to a car accident with truck, lots of energy losses there. So the main fundamental, right, behind this classification of the collision is energy loss. Energy loss will define, right, the nature of the collision, and energy lost will actually classify, it will help us in, right, the classification of the collision. First, no energy loss. See, to understand this example, so to understand this stuff, let's take an example first, then we are going to write down the noteworthy points. Suppose, let us take a very simple example, right? This is particle 1, mass m1, moving with velocity u1. This is particle 2, mass m2, and moving with velocity u. This is the situation before collision. After collision, this is mass m1 moving with velocity v1. This is mass m2 moving with velocity v2. Before collision, after collision. Before collision, after collision. Before collision, velocities were u1 and u2. After collision, right, velocities are v1 and v2. My question, is there any kind of the energy loss or not? Suppose if I'm taking the example of the billiard balls, they are moving forward. If the two collides and after collision the velocity is getting changed, in that energy loss is minimum. No energy loss. Theoretical, we are having no energy loss, right? So that case is of the elastic collisions. So in elastic collisions, in elastic collisions we are having no energy loss. The kinetic energy of the system before and after is same. Kinetic energy is conserved. Second point. I'm talking about the system. If I'm talking about the whole system, right? If I am talking about the whole system, net external force is 0, right? Net external force is 0, right? Net external force is 0 for a system. It means momentum is also conserved. Right? Elastic collisions, no energy loss theoretically. Kinetic energy is conserved, right? Net force on the system is 0. It means momentum is also conserved. In inelastic collision, energy loss is there, right? In inelastic collision, right? Okay, energy loss is there, right? Kinetic energy is not conserved. momentum of the system is conserved. Kinetic energy is not conserved because energy loss is there, but momentum of the system is conserved. Perfectly inelastic collision. Maximum energy loss. The first particle sticks to the second after collision. Car accident. First, it gets sticked. Maximum energy loss. Particles stick together. This is a word, right, that is used for inelastic collisions, right? Sometimes in question it is not mentioned which type of the collision it is. So for that we are having the specific word. Particles get stick together. Maximum energy loss, particle gets stick together. Kinetic energy is not conserved. Momentum is conserved. But momentum of the system is conserved. Right? See, first of all, we moved on to what actually the collision is, right? After we saw this classification. But this classification is based on the energy loss and some of the noteworthy points. Now, I want to actually define the nature of the collision. For that, we are going to use the same example. Before collision, particle is of mass m1 moving with velocity u1, particle is of mass m2 that is moving with velocity u2. After collision, particle of mass m1 that is moving with velocity v1, particle of mass m2 that is moving with velocity v2. So before and after collision. Before and after collision. Apart from energy, right? Apart from energy loss, right? The coefficient of the restitution, this will help us to determine the nature of the collision. So the actual formula of the coefficient of the restitution is, right, E is velocity of the separation by velocity of approach. This is for one, or you can say one particle system that is colliding with some stationary object or of the heavier mass. The another formula for the two particle system, we can define it as E is equal to V2 minus V1 whole divided by U1 minus U2, right? The terminology stands same that has been abbreviated in these examples. It means U1 that is particle 1 initial velocity, U2 particle 2 initial velocity, V1 particle 1 after velocity after the collision, and V2 is, right, velocity of the particle 2 after the collision. So this is what the coefficient of restitution, like coefficient of friction, how surface, how rough the surface is. That's coefficient of friction. Coefficient of friction, static friction, how the surface is having the ability to hold an object, right, even while the external force is applied. That coefficient of static friction, that determines the nature of the roughness of the surface. Similarly, coefficient of restitution, that determines the nature of the collision. If it is elastic collision, the coefficient of the restitution value is 1. It means that velocity of separation is equivalent to velocity of approach. If it is inelastic collision, the coefficient value is in between 0 and 1. Velocity of separation is not equivalent to velocity of approach. Right? Here, velocity of separation is not equivalent to velocity of approach. Right? Perfectly inelastic collision, coefficient of restitution is 0 and velocity of separation is also 0 because the particle gets stick together after the collision. So this is what the entire detail, right, of the collision is all about. We have defined the collision in terms of energy conservation. We have defined the collisions in terms of the coefficient of restitution, right? We determine the values of the restitution also. But there are some two important formulas related to it, right? Two important formulas related to this collision and things are getting resolved. First, Again, we are going to take the same example, right? We are going to take the same example. This is a situation before the collision and this is a situation after the collision. In all of the types of the collision, the system, on the system, the net external force is zero, so momentum is conserved, right? For all type of collisions, momentum is conserved, but only for elastic collisions, the kinetic energy of the initial and final kinetic energy of the systems is conserved. And for rest, there is an energy loss. See, before particle, this was mass m1, this was moving with the velocity u1, this is m2 that was moving with the velocity u2. After collision, this is m1, right, it is moving with velocity v1, this is m2, right, moving with velocity v2. We need a common formula of a particle, right? This kind of the questions are there into the examination, right? And they are asked as a PYQ. I'm going to show you all just after this derivation, right? Now, we are in need of a formula that can be used, right? That the general formula for all types of the collision and that can be used to solve this sum easily. Net external force on the system is zero, momentum is conserved, right? Can I write it down? Momentum is conserved, so m1 u1, m2 u2, that is equal to m1 v1 plus m2 v2, right? In lots of books, lots of derivations are given, but into the very few resources, right, this formula is mentioned and it is a very important one. What will be the value of the coefficient of restitution? v2 minus v1, and that is equal to u1 minus u2, right? This is what the restitution is. Okay, now e u1 minus e u2 plus v1, that is equal to v2, right? The main motive for this derivation is, right, to find the velocities of the object right after the collision. General formula. So can I consider this as equation number 2, replacing equation number 2 in equation number 1, right? Replacing equation number 2 in equation number 1. What we get, right? That is m1 u1 plus m2 u2, right? Can I replace the value of the m1 v1 plus m2 e u1 e u2 plus v1, right? Now we need to solve this. m1 u1 m2, right, u2 is equal to m1 v1 plus m2 e u1, right, minus m2 e u2 plus m2 v1, right? From this we need to identify the value of the v1. So here it is m1 u1, right, and minus, okay, m1 u1, okay, plus m1 u1 m2 u2, so anything v2 e u1 minus e u2, okay, so here minus this term m2 e u1 plus m2 u2, right, and this is plus m2 e u2, that is equal to v1 m1 plus m2. From this, velocity of the first particle after the collision, that is m1 minus e m2 whole divided by m1 plus m2 u1 plus, right, m2 1 plus e whole divided by m1 plus m2 into u2. This is the velocity of the first particle after the collision. First particle after the collision. Now this is a generalized formula, right? If elastic collision is going on, replace the value as E is equal to 1. If inelastic collision is going on, replace the value of the E will be in between 0 and 1. If inelastic collision is going on, replace the value of E as 0. Now, again, rewriting this equation, right, we'll get v1, that is equal to v2, minus EU1 plus EU2. Can I replace this equation in equation number 1? So to get the velocity of the second particle after the collision. So it is m1 u1 plus m2 u2, that is equal to m1, right? What it is? v2 minus eu1 plus eu2, right? Plus m2 v2, right? So we are replacing all of those stuff, right? We are replacing all of those stuff to get the equation velocity of the second particle after the collision. And finally, I will rewrite this equation above, right? Finally, right, I will rewrite this equation above, right? I'm going to rewrite this equation, okay? Don't get worried. So now here it is m1 u1, right? Okay, plus m1 e u1, m2 u2 minus m1 e u1, right, is equal to m1 plus m2, right, v2. So we are getting the formula of v2 as, right, m1 1 plus e whole divided by m1 plus m2 u1 plus m2 minus e m1 whole divided by m1 plus m2, right, u2. This is the velocity of the second particle after the collision, general formula, right? I'm writing down above, right? So it will be quite helpful for you all, right? See, before collision the velocities were u1 and u2. We need to calculate the velocities after the collision. So using the conservation of momentum and the coefficient of restitution approach, we got the velocity of the first particle after the collision as m1 minus e m2 whole divided by m1 plus m2 u of 1 plus, right, m2 1 plus e, right, u2 whole divided by m1 plus m2. This is the velocity of the first particle after the collision. Velocity of the second particle after the collision is here, that is m1, right, 1 plus e whole divided by m1 plus m2 into u1 plus m2 minus e m1, right, whole divided by m1 plus m2, right? Okay, this is u2. This is the velocity of the second particle after the collision. Directly you can use, and we are going to use this stuff, right? So this is all about the momentum of the kinetic energy. Even you want to write down the kinetic energy, right? Then initial, okay, kinetic energy initial, that is equal to half m1 u1 square plus half, right, m2 u2 square. Final kinetic energy, that is equal to half m1 v1 square plus half m2 v2 square. This is all about the kinetic energy. But why we are not dealing to that stuff, right? Because this thing is, right, conserved only in elastic collisions, right? So this is what the collisions is all about, right? This is what the collision is all about. Initially, right, we see the collision is the nature of the collision, the restitution, the classifications of this, the momentum and kinetic, and we got the two important formulas. Okay, all see, two interacting particles masses are given, nature of the collision, right, the restitution is given, u1 and u2 is given, you will get v1 and v2. With this you can get the fractional kinetic energy loss also. See, using this equation, right, we are going to solve that stuff, and this kind of how that formula is going to helpful, right, in solving the question that has been already asked in NEET 2019. We'll see. See, a body of mass 4m is moving with, a body of mass 4m, it is moving with speed u, and it collides with another body of mass 2m, right, which was at rest. So before collision 4m was moving with u, after this 2m was at rest. Right. Now it has been given that collision is completely lasting in nature. Then after collision, the fraction of kinetic energy loss will be what? So for that, we need to calculate the velocities of the particle after the collision. Now we need to calculate the fractional kinetic energy of body A. It means we need to calculate velocity, right, of A after the collision. Now nature of the collision, it is given as completely elastic. It means that simple, right? We want to directly replace the formula. So velocity of the A after the collision is V1. What is the formula of V1? M1 minus E M2. See, M1 minus E M2 whole divided by M1 plus M2, and that is U1 plus M2 1 plus E, right, whole divided by M1 plus M2 into U2. Now U1 are initial velocities of the particle. U1 is U, U2 is 0. Now if U2 is 0, then this entire part is going to be 0. Because here U2 is 0 and 0 is multiplied with that stuff. So what will be the value of V1? M1 is 4M. Restitution value is 1 because it is an elastic collision. M2 is 2M whole divided by 4M plus 2M, right, into the velocity U1 is U. So V1 that is equal to 4M minus 2M by 6M into U. So V1 velocity of the collision is U by 3. Velocity before the collision was U. Yes, right. It collides with a particle at rest. The velocity of the collision was U, but after the collision it got U by 3. So what is the fractional kinetic energy loss? The difference, right? That is half M V final square minus V initial square whole divided by half M V initial square. Replacing the values, you will get delta K as 8 by 9. Sorry, delta K by K, the fractional energy loss, right? C is a perfect answer. So see how this formula is quite helpful in solving that stuff. There is one assumption also, not assumptions, it is a perfect result. Suppose if this is a mass M, this is the mass M. Initially it was moving with U and this was at rest. What will be the velocity of the first particle after the collision? V1, M1 minus E M2 whole divided by M1 plus M2, right, U1 plus, right, M2 1 plus E, right, whole divided by M1 plus M2, right, into U2. U2 is 0. So V1 it will be right, M minus M whole divided by M plus M into U1. Similarly, if you are applying the formula of V2, then you are going to get as U. What it states, before collision, U1 was U, U2 was 0. After collisions, right, V1 is going to be 0, right, V2 is going to be U. See, velocities got interchanged. Why it happened? It happened only in the case of elastic collision, right, and for the identical masses. In the case of elastic collision and only for the identical masses, right, in case of elastic collision only in the case of identical masses, right, elastic collision, right, whenever the two identical particles are colliding elastically, perfectly elastic, like perfect elastic collisions are going on, then obviously they will, the velocities right along the line of motion will get interchanged. Velocity vectors will get interchanged, right? Not only the values or magnitudes, velocity vectors will get interchanged, right? Okay. So this was the more important stuff, right, that I want to discuss. Now, second question. This question based on the coefficient of restitution that has been asked in NEET 2018. A moving block having mass M collides with another stationary block. See, a moving block mass M, right, that collides with another stationary block of mass 4M at rest. The lighter block comes to rest after the collision when the initial velocity of the lighter block is V. Right, then the value of the coefficient of restitution is what? Moving block of mass M collides with stationary block of 4M. See now, coefficient of restitution is velocity of separation by velocity of approach. It is equal to V2 minus V1 whole divided by U1 minus U2. right? Now, see what it states, right? Initially, M was moving with V, right? 4M was at rest, right? M was moving at the V, right? Okay, so can I say U2 as 0 and this was moving as U, or you can say as V, eraser. This is V, right? Now it has been given the lighter block comes to rest after the collision. It means V1 is 0. V1 is the velocity of the first block after the collision. It has been given 0. While U2, the velocity of the second block before the collision is 0. Both things are mentioned. Now we need to calculate, right? We need to calculate what? The coefficient of restitution. Still we are having V2 as unknown. The velocity of the second block after the collision. Directly we are using this formula, right? But still we are not having that. Okay, so we can apply the coefficient of restitution, this momentum conservation. M was moving with V, right? Finally, plus 4M was at 0. This is initial momentum. Final momentum M got to 0 plus 4M got the velocity of V dash, or you can say V2. Right, so this V2 that will be equivalent to V by 4. Replace this, right? E will be 1 by 4, that is equal to 0.25. Right, the B is a perfect answer for this specific question. See, this is how the momentum is going to help. This is how the coefficient of restitution is going to help, right? This is how the equations are going to help, right? Okay, lots of things, right? They are going to help. Apart from this collisions, right, there is one more important concept, right, for the 2D. Basically, the classification of the collision is based on 1D and 2D, right? Basically, the classification of the collision is completely based on, right, 1D and 2D. In 2D, there is one simple question solving approach that is going to help us a lot. Only single question solving approach. What it is? Particle is coming with velocity u, making angle alpha. It collides here. I'm not saying which type of the collision it is, and reflect back. We need to generalize this and obtain the formula as we did into the previous part of 1D. Right? Previously it was completely the head-on collision we discussed. Right? We completely a head-on. This is all about the head-on collisions, right? Apart from elastic, inelastic, right? See, elastic, inelastic, perfectly inelastic. Apart from this is having 1D, 2D, 1D, 2D, 1D, 2D. 1D, 2D, this is all about the 1D means head-on collision, right? The line of the motion of the particle is same. That is head-on collision. And this is everything we discussed about this stuff is about the head-on collision. See, collision in 1D, right? But this you all are aware of, right? The most important stuff regarding the collision is this formulas and whatever the things related to 2D what I'm discussing right now. See, right now I'm not aware of what kind of the situation, what kind of the collision is, what will be the value of E, right? But we are saying this. Suppose it collides and it reflects back to angle theta. We need to calculate the theta, right? And this. See, now, when the two particle collides, right? There are always the two most important factors. The first important factor is common normal. The normal that is common to the two surfaces. Let us take an example. Suppose this particle is moving on this way and this particle is moving on this way. They both collide like this way, right? So this will be the common normal for them. And this will be the common tangent. Normal reactions. As you can imagine normal reactions like that common normal. That tangent that is common to them, it is a common tangent. Again, I'm showing you one example to understand this stuff, right? Again, I'm showing you one example to understand this stuff. Suppose this particle is moving on this way and this particle is moving. They both are going to collide at that, right? So this will be, right, the common normal and this will be the common tangent. It is important, right, okay, to understand the concept of common normal, common tangent. Common normal for two colliding, two interacting particles, right, the line that is actually normal to both. Common tangent, right, the line that is actually a tangent, the common tangent to the both interacting particles while collision. This is happening common normal and this is common tangent, right? This is while collision, not before and after collision. This is while collision, and this is only the concept to solve the sums, right, of 2D collisions into the quite convenient manner, right, of the 2D collisions into the quite convenient manner. While collision, the common normal to the both, the common normal reaction that lies to the line, that line is a common normal and common tangent to the both, right? Now, suppose this is a u sine alpha, this is a u cos alpha. Similarly, when it reflects back, right, this is a x component, this is a y component. Now, first most important point, right, the components of velocity that lies along common tangent never get changed. Tangent is not going to create an impact into the collision. Only the normal, see, if two particles are colliding like this way, right, then the normal between them is only going to create an impact, and it is only the responsible for the energy loss. So it means along the common tangent u sine alpha, it is not going to change. Neither the magnitude is going to change, neither the direction is going to change. But second point, momentum is conserved for components, the velocity components that lie along common normal, not common tangent. Momentum is only conserved for a particle that lies along the common tangent, common normal. Coefficient of restitution formula is only applied to velocity components that lie along common normal, not common tangent. It means the coefficient of restitution said velocity of apparition by velocity of approach. So this will be the y component e to the velocity of approach. What is the velocity of approach? The component that lie along the common normal, that is going to create an impact. So velocity of separation is e v cos of alpha. Sorry, e u cos of alpha. So the y component after the separation is u cos of alpha. Right? So what is the velocity of the particle after the collision? That is equal to u sine of alpha of I plus eu cos of alpha of j. You can see the component that lie along the common normal changed e times. This thing you can see changed e time. Now e completely depends on the value, whether it is 1, whether it is e 0 is less than 1 or everything, right? It completely, it will define the nature of the collision. So this is the best question solving approach of the 2D. For that, right, you need to understand the concepts of the common normal and common tangent. Right? So guys, be aware of it. right? If someone right is not able to understand this stuff, guys, I'm going to tell you all, just kindly rewind this video and see this again. Okay, because this collisions again we are going to discuss into the center of mass also with the combined rigid bodies. This is a case of the rigid bodies 2D. This is just for an information purpose, right? Apart from this, we have discussed lots of things, right? Head-on collisions and everything. This 2D is just for the discussion purpose. So the reason behind it is because we haven't dealt with the rigid bodies till now. And so if we haven't dealt with the rigid bodies, so we are not going to understand this stuff of 2D. What actually the common normal is, but still, right, you can rewind the video multiple times for this concept, right? You can see this stuff. Okay, so and from the beginning of the chapter, right? Okay, there are some homework based questions, right? But let's have the glimpse of it, right? Okay, we started with the work, energy and power, right? We moved on to this flow chart of this chapter, right? We moved on to some of the important concepts related to the work done, right? Okay, conservative forces, non-conservative forces, right? Spring forces, right? Some of the most important formulas, right? Let's have the glimpse of it, right? We did all of those stuff, right? And after that, we moved on to the work done by different forces, but it's okay. But I think everything is included into the work energy theorem, right? Some of the important concepts related to and steps how to solve this, right? Questions. Motion into the vertical circle, we also saw that after, right? First of all, we moved on with some of the most important concepts related to the work energy theorem, right? And after that, we moved on with the chain problems. One chain problem I show you all, and two I gave you all a homework, right? After that, we saw the motion into the vertical circle concepts and sums related to it, some of the important formulas. And after that, we moved on to the power is a different thing. It's not a big deal. Right, whatever the questions you are saying, it will be available into the PDF, right? You can download it from the app and you can have that stuff to solve as a practice, or lots of things, lots of questions are available in this presentation, right? Because of the limitations, time limitations, right? Okay, but you can do it by your home, by yourself. So nature of the collisions, energy loss, this is all about the momentum and kinetic energy of the 1D collision, right? After that, we discussed the 2D collision, right? And some of the sums are related to it. Okay, now so guys, this was from my side, right? Thank you all. This was all about the work, energy and power, right? I will be waiting for all of your comments. I used to read all of your comments, but I never reply on that. So guys, this is Indrajeet Singh, right? So I must say thank you for all of your love that you have showered in my previous videos. For this video also, I will be waiting for all of your responses beneath the video. Kindly do comment, right? It acts like a motivation for us. Okay, so guys, this is Indrajeet Singh. It's time to go. Again, we will come back with the new session with the new teaser. Hope so for today's session, right? We made a teaser. Hope so you liked it, right? So again, we'll come back with the new stuff for a rotational motion, right? So this is Indrajeet Singh, right? Signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bacha ji. Bye everyone. Stay at home, stay safe, stay healthy amidst the pandemic. Bye.